Hello, am I audible? Hello.
Yeah,
Yes, ma'am, you are audible.
yes, sir.
So let's wait for 5 more minutes and then we'll start.
Ma'am, you are not audible.
Yeah, actually I'm not saying anything. So still people are joining, so let's wait up to 8:10 maybe. I'll start from 8:10.
Ma'am, I have doubt in Riemann sum and Floyd-Warshall and Warshall algorithm. These three would you discuss today?
Okay. So in
Can you
Meenakshi,
please
what's your doubt?
can you can you please brief in explanation concept, ma'am? Week 10 out of 11.
Sorry, what?
Concept, ma'am.
Yeah, I'll cover all the concepts from week 10 and 11.
Yeah.
Ma'am, one small question, ma'am.
Yeah.
Suppose I am given a function, say x cube or x to the power 5.
Uh,
So how many number of turning points will that have? X cube or x to the power 5? Just a doubt.
so see, it's x cube or x to the power 5, right?
Yes.
So the graph of such polynomials are very easy. So if you have any even degree polynomial, even degree function,
What
suppose,
degree? This
yeah.
odd.
So if you have x to the power 5 or x cube or x to the power 7 or x to the power 9 or any odd degree, right?
Yes.
So then that polynomial, then the graph of that polynomial look like something like this.
Yes.
The only change will be here, there will be much more thicker part if you change the power. So that means in x cube, you won't find out much more thickness here around the x-axis. Right.
Yes.
So here there is no turning point. Right. So we know what is the turning point. So a turning point is when
If
the
the power is even.
yeah. So if the power is even,
Mm.
then we have a turning point, because then it will be, then the graph will look like this. Right. So
Okay.
here there will be one turning point.
Okay. And even if it is shifted by 1 unit or 2 unit, it does not matter. It does not have any turning point, right?
Right.
Yeah, one thing more. There was a question in the practice assignment, e to the power x minus e to the power minus x by 2. This was
Uh,
a function and it showed a parabola. Why?
e to the power x minus,
E to the power minus x by 2.
it showed a parabola.
It showed a parabola. It was e to the power x plus e to the power minus x or minus e to the power minus x. I don't clearly remember, but either of them, it showed a parabola.
So
Why?
you check this by Desmos?
Desmos also shows a parabola, but
Hmm.
actually I do not understand how it came.
See, it's a combination of functions. So it may happen that it will be a parabola because see, e to the power x graph, if you observe, then it's something like this. Okay. And then we have minus of e to the power minus x's graph. So e to the power minus x's graph, if you change the sign simply this, that means e to the power minus x's graph, then this graph will look like something like this. And if you add minus sign here, so all the values, whatever positives are there, it will look like something like this. So this is the graph of minus of e to the power minus x. Now we have addition of these two graphs. So it may happen that it will create a parabola, right? We don't know. So it may happen that it can create a parabola. It will look like parabola, but it's not exactly parabola. Then the values are different. It won't be similar to some x to the power even power, right? It will be little bit similar, but it's not exact the parabola. So what's your doubt here? It can happen that this look like a parabola.
No, actually, the functions like this were given and the graphs corresponding to them were given. So it was on the practice assignment, and I saw in Desmos and found it was parabola, but I actually wanted a justification for it so that such a graph, if it comes in the exam, I can see it is a parabola or not, or is there any proof
Okay.
that it goes and becomes a parabola?
No, see, when we have such kind of combination, when we have two different kind of graphs and we have some addition or subtraction, in that case, it's very difficult to judge a graph of any function, right? So if some question is given in which such kind of complicated function is there, so you should know that, okay, the graphical method won't work here. If you just have e to the power x function or the single function, you're understanding the single function or the
Yes.
combination of mod at max, that means modulus of e to the power minus x or something like this. If we have a only single function, then we can apply graphical method. But if we have a combination of function in which we have addition, subtraction or something like this, then it's very difficult to judge a graph. The only way is Desmos only, because Desmos, what it does, it actually, I think it compute the values, I mean for each x it will compute a y and then plot it in the graph. So that's what Desmos do, and that's a fair thing, right? The computer can do it because, but we cannot find a value for each x and then put a graph and then make the graph, right? So so the conclusion is, if such kind of function is there, you don't have to go through the graphical methods. If there is very simple function, that means a function with a combination of mod, and it means modulus of log of 1 plus x, which we saw in the quiz too, right? Or something e to the power 2x or e to the power x square or e to the power modulus of x, something like this. If such kind of things are happen, then you have to go via the graphical method. But in this case, don't go via the graphical method.
Okay, ma'am. One more question, ma'am. 2 to the power log m log base 3 m. 2 to the power log base 3 m is
Huh?
equal to m
To the power log base
log
3
base
to
2. Is this
yeah
provable? Means it was in the last paper, and
yeah, it is a
got
property of logarithm.
it is a property of logarithm.
So this is a property. You can prove it. I haven't discussed the
No,
proof
I
of.
don't require a proof. Is it true? Then I will use it. That is
Yeah, it is true. It's true.
okay. And what was the next question? Uh, mm, just a second. Mm, well, I will tell you later.
Okay, yeah, fine. So let's start with the. Okay, first
Yes. One more question. The question was that suppose an adjacency matrix is given, and I have to find if a point is reachable from one point to other, right? So in that case, breadth first shot, depth first shot is okay, but suppose sometimes that a1 plus a2 a squared plus a3 up to an is given, then should I go on multiplying even a fourth size matrix would be very hectic to do. Is there any shorter path than that?
Yeah. So see, if an adjacency matrix is given to you, and suppose you are saying that 4 by 4 matrix is also tough to handle by BFS and DFS, right? That's your concern, huh?
Yes, no, means if there is a path, it has to be A1 plus a square plus a3 up to, yeah, up to
Yeah.
4 is, so you have to multiply it 4 times. So it would be pretty complicated for
Right.
one.
So in that case, yeah. So yeah, right. I'm now I get. So you want to compute a plus, right? So you are
Yes,
saying that if I compute a plus, then a plus is nothing but a plus e square plus e cube and plus e to the power 4, right?
yes,
So don't go via this method. I know it's a well-defined method, but it's only for computers because we can program a matrix in computer. If we are a human, then obviously for finding a square, a cube, and e to the power 4 is a very hectic job for 4 by 4 matrix even. If you take 4 by 4, forget about 3 by 3 is there, still we cannot figure it out,
yes.
right? So in
So,
that case, what you have to do is just make a graph from this matrix.
okay.
That will reduce the problem very much. I mean, it's very easy now because we just have 4 vertices and we have to look a path. So we know how to compute the graph of from this particular matrix,
Okay.
right? Yeah. Even though it's a correct method, but still it's a very long process.
Very
Finding
lengthy
q e to
process.
the power 4 and so
Ma'am,
on.
we check through graph method like from I to J we need to go if we need to find a, a point K for A square and K comma L for A cube like that. Can we do
Yeah,
like
yeah.
that?
So that means at least one of these I comma jth entry, I comma kth entry, if you want to find out the path from I to k, should be equal to 1. That's the meaning of a square, a cube, and e to the power 4, right? So if there is I mean, if a's I comma kth entry is 1, so that means I and k are related via an edge. And if a square of I comma k entry is 1, that means I and k are related via some other vertex j, right, using two edges. So this method, it's okay, it's work, I mean it will work, but as a human or in the exam, it's very lengthy method if you want to apply this, because for finding a square, a cube, e to the power 4 is very tough. But in the programs in the computer, we have a particular I mean, if you just give a computer a, then it can calculate its power very fast. If you want e to the power 100, it will give you in a second, right? So this method, it's not applicable if we are in an exam and if we have to compute it by our hands, right? So it's better to go with just create a graph from that matrix and then answer the question. That will be much more easy and helpful.
Excuse me, ma'am, one more question. That
Okay.
was, suppose I am given a BFS tree, then how will I find which are the possible edges and which are not the possible edges?
Yeah,
And
I'll discuss
DFS.
this one. I'll discuss this one in meantime. Okay. So let's,
Madam, sorry to interrupt. So
yeah.
today, what is the plan, madam? So, because it should be beneficial, instead of addressing individual queries, maybe there is more mediums are there.
Yeah, yeah, yeah.
So the majority of students beneficial manner, maybe if you are,
Right,
yeah.
right, right. So I have a plan that first I'll go through main major concepts. So that means whatever main concepts are there in week 10 and week 11, we discuss those methods with some examples. And then at the end, I'll take individual doubts. So if no one has doubt, then he or she can leave the session, right?
Oh, thank you, madam. Thank you.
So I'll start with a basic. So I won't recall the basic definition. So you guys know what is a graph, what is a vertex, what is the degree of vertex. Okay, so I'll start with vertex cover. So I hope that will be fine for everyone. So what is a vertex cover? So vertex cover is nothing but a subset of a set of vertices. So let me know if I'll move a bit fast. Okay. So subset of a vertex set. We know in a graph we have two type of sets, vertex set and edges set. So what is a vertex cover? So vertex cover is nothing but a subset of a vertex set V in such a way that
Ma'am,
it will cover.
from which week we start?
Sorry, what?
From
From
which
week
week
10.
you?
Week 10.
But ma'am, you left from week 6, I think.
Uh, is that the case? I mean, I have informed that, I mean, you guys are done revision
No, ma'am, no.
up to week 9.
Oh, ma'am, time gets over and we left it from week 6, I think.
Okay, so
Week
I'll
five.
cover the graph till you complete.
Till week 4 she done.
Yes, ma'am.
Till week 4.
Yes, please ask her.
Okay.
Ma'am, in calendar Tomorrow there is a revision session from week 5 to
Actually,
week
ma'am,
9.
please start the week 10 and
Yeah, I'll cover week 10 and 11, and if there is no revision session for the remaining week, then we'll figure it out something, right?
Ma'am, if you
Tomorrow
want
there is a
to
session, ma'am.
over, then you can start from week 9.
Actually, I
Ma'am,
planned
if
for
you
week
don't
10
mind,
and 11, and week 10 and 11 will cover, more questions will be there from week 10 and 11. So
ma'am, if you
So
don't mind, will you
better.
cover from starting
No, it's
yeah,
from
very
basic?
late.
starting means, yeah, it's a concept from lecture 10.2. So I think I haven't skipped. I just skipped the basic definition. I mean, you know the graph, what is a graph, what are the problems, reachability problem, and all those things. I haven't skipped any.
Ma'am,
Yes,
but
yes,
ma'am,
please,
week
please
9
continue.
is week 9 is like flow for week 10 and 11. Some of the
please continue.
topics are I can't understand from 9 10.
Okay, so
Week 9
there
is
is a
a
session
different part.
for week 5 to 9.
Yeah, I know.
Yes, yes, yes.
Yeah.
Okay, ma'am.
Please continue, ma'am.
Fine.
Madam,
We'll
see,
continue with week
based on the
10.
calendar, so 10 and 11, it's to mention. So based on that, people maybe larger people maybe they're interested. So based on the calendar, they're aligning. So maybe for 5 to 9 tomorrow will be there. So
Yeah, tomorrow.
yeah, so
Okay.
those will be get the benefit for tomorrow.
Yeah.
So maybe you can
Yeah.
continue with your plan.
Continue, ma'am. Continue.
Please, thanks.
Okay, fine. So let's start with vertex cover. So what is a vertex cover? So it's nothing but a subset of vertices, but we have to consider a subset in such a way that it will cover all the edges of the graph. So what is the meaning of covering? I'll explain it by example. So vertex cover is nothing but a subset of in such a way that it will cover all the edges. So for example, if I have a graph like this, okay, so suppose this is my graph, and here there are some vertices up to 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so in that graph, there are so many vertex cover can happen, right? So one vertex cover I can make, again, I'll say vertex cover is nothing but a subset of V which will cover all the edges. So here it's your choice which subset you want to consider. So one can say that, okay, I'll consider the V itself. So that means if you take all the vertices, that will also form your vertex cover. So that means if I take VC1 means the first vertex cover, the example of first vertex cover. So here I am taking all the vertices. So all the vertices from 1 to 9. So what happened here? These all vertices will cover all the edges. So that means if I consider 1, in my vertex cover, then this 1 will take care of this edge. So that means if I am considering 1, this edge will be covered. If I am considering 2 in my vertex cover, then this edge will be covered. If I am considering 3 in my vertex cover, then this edge, and this edge will be covered. It doesn't matter if a edge is covered twice. Okay, it's okay. In a vertex cover, this can possible. But ultimate goal is we have to cover all the edges, right? So similar with all those vertices. If we consider these vertices, then whatever edges are adjacent to those vertices, those will be covered. That's the meaning of covering the edges. So if you consider this subset, then this is also a vertex cover. So here it's kind of trivial that we have one vertex cover, and that vertex cover is nothing but the subset of vertices itself. So here the question will become, okay, so then now what will be the minimum number of vertices we need to make a vertex cover? Okay, so and it so happen that this minimum number is unique. So that means if you give this task to so many peoples and ask them what is the minimum number of vertices we need to form a vertex cover, then that number is nothing but unique, and that number is one. This is the question we want to answer. And what is the minimum number of vertices we need to form a vertex cover? Okay, so here let's try to judge what are the minimum number of vertices we need to form a vertex cover. Okay, so here you observe that for covering this edge, okay, so for covering this edge, I need to consider either the vertex number 1 or vertex number 2. Okay, but here if I consider vertex number 1 in my vertex cover, then only this edge will be covered. There is no other extra thing this particular vertex number 1 is giving to me, right? So, but if I consider vertex number 2 instead of vertex number 1 in my vertex cover, okay, so here now my motto is to find out a vertex cover with minimum number of vertices. Okay, so may vertex cover. This is also known to be minimum vertex cover. minimum number of vertices. Okay, so here if I consider 1 in my vertex cover, then there is no benefit. It will cover only one edge. But instead of 1, if I consider the vertex number 2, then it will cover this edge and this edge too. So that means it's okay. So for covering this first edge, I need to consider either 1 or 2. So I'm considering 2 because 2 is covering 2 edges. 1 is covering only one edge. That's why I'm starting with 2. Now let's go to the next vertex. So here also, if you consider 4, then only this edge will be covered. So that's why the only so that means what will be the benefit? I mean, if you want to cover this edge, you have to consider either 3 or 4. So if you consider 4, again you will get only one edge which will be covered by our vertex set, right? So that means it is okay if we consider the vertex number 3, because vertex number 3 will cover this edge and this edge too. So the next vertex in my vertex cover will be vertex number 3. Okay, now similarly, let's go to the another vertices. So here also, if I consider 9, then this edge only covered. So that means I have to consider either 9 or 5. But 5 is covering more edges than the vertex number 9. So that's why we take 5 in our vertex cover and leave the vertex number 9. So now, how many edges are covered? So this edge is also covered because we are taking 5. So this edge is associated to 5. That's why it is covered. Now we have taken 5. That's why this edge is also covered. Now we have to cover these 2 edges. Okay. So now there are 3 choices are left. So either we can take 6 and 8, but again we want minimum number of vertices. So if we take just vertex number 7, then vertex number 7 will take care of covering these 2 edges too. Right? So that means we have to take vertex number 7 in our vertex cover. Now using these 4 vertices, we can cover our graph. We can make a vertex cover which will cover the whole edges. Every edge in the graph. Okay. So let's recall what are the vertices we have taken. So we have taken 2, 3, 5, and 7. Okay. So our vertex cover is now 2, 3, 5, and 7. And the process I just tell what should be your aim to consider a vertex. So that means you have to consider a vertex in such a way that it will cover more number of edges. So if we take 2, then this edge and this edge is covered. If we take 3, then this edge and this edge is covered. If we take 5, then this edge and this edge is covered. And if we take 7, then this edge and this edge. So that means if I want to cover this graph, then I need at least 4 vertices. And this is a minimum number of vertices. Minimum number of vertices. Okay. Because if you remove one of the vertex from this, there will be edges which won't get covered, right? So this is our minimum vertex. Now again, it's not unique because here we have choices. So suppose in place of no, I think in this case it may be unique because the graph is very easy. But there are some cases where you can find more than one number of vertex cover with minimum number of vertices. So
And
that's
here also there is a change. You can change 2 to 1. Still the vertex cover.
Yeah, correct. Thank you. So here also we can change, right? So because 3 is taking care of this edge. So in place of 2, if I change 1, then that's also fine. Correct. So that's the reason that vertex cover is not unique, but this number is unique, that we need 4 vertices. Right? So we need 4 vertices. So this number is one thing we want to compute. So the question will be formed that what is the minimum number of vertices we need to cover a graph, and that in this case the minimum number of vertices is 4, and that can be solved by vertex cover. And this concept is explained in the lecture by CCTV cameras. So if you guys have if you guys want that explanation, you can go and check it out. Okay, fine. Is there any doubt in vertex cover?
Ma'am, only by estimation that which edges will be covered, I have to find out vertex cover. There is no separate formula or something like that in the graph.
Actually, there are algorithms, but it's much more complex. So it's not covered in our course. So we just have to go by our intuition. That's all. Okay. There's no specific method so far.
And independent set also same.
Yeah, same thing for independent set, same thing for
Matching.
matching, same thing for coloring also.
Okay.
Okay. Now let's go to independent set. So what is an independent set? Again, it's also a subset of vertices. So you can say that it is a subset of non-adjacent vertices. Subset of non-adjacent vertices. Now, what are non-adjacent vertices? So if two vertices, so suppose this vertex and this vertex, if these two vertices are related by a direct edge, then those vertices are known to be an adjacent vertices. Adjacent means you can say the neighbor or connected by a single edge. Now, if there are two vertices which are not related by a single edge, so suppose these are two vertices A and B. Now A and B are non-adjacent vertices because they are not related by a single edge. So such kind of vertices are known to be non-adjacent vertices. So independent set is nothing but any subset of vertices in which every vertex is non-adjacent to every other vertex. Okay, so here, if you consider this example, so here in this example, let's try to find out what is the independent set. Okay, so I'll ask you guys, if I consider this set, so suppose I consider 1, 3, 5, 6, and 8. Is this an independent set?
No, ma'am.
No, ma'am. 5 and 6 are
Correct. 5 and 6 are adjacent vertices. They are connected by an edge. That's why this is not an independent set. So independent set means every vertex should be non-adjacent to every other vertex in that particular set. Now it's kind of trivial that if I consider a set, suppose I take a set with only one vertex, right? So suppose I'll take only vertex number 1. Then this is one possible independent set. So again, there is an existence of independent set in every graph. So what will be our question here? So our question here is what is the largest independent set we can form? Or what is the number of vertices we can use to form an largest independent set? So that's the question we want to ask. So here the question will be, what is the cardinality, or what is the largest
Ma'am, a
independent?
small clarification. Even one is a single pair, or like single set of one is also independent set, right?
Yes, single set of 1 is also, because see,
Okay.
for vertex curve we just need for independent set we just need two conditions. It should be a subset of vertex set, and every vertices should be non-adjacent. So here there is no other vertex for comparing the non-adjacency behavior. So yeah, it's an independent set. That's why existence is there. Now the question will be that what will be the largest independent set we can form? That's our question. Okay, so let's try to guess what will be the largest independent set in this particular graph. Okay, so here if I consider vertex number 1, then the adjacent vertex to vertex number 1 is only vertex number 2. So that means if I take 1, then I cannot take 2, but I can take every other vertex. But if I take 2, then I cannot take 1 in my independent set, and I cannot take 3 in my independent set. So that means choosing 2 will reduce the number of vertices by 2, right? So if you choose 2, you cannot take 2 vertices, which are 1 and 3. But if you choose 1 in your independent set, you cannot take only one vertex. So that means here we are just discarding only one vertex. So here our benefit, we can have a benefit by choosing 1, by not choosing 2, right? So it's better to start with vertex number 1. So if I choose vertex number 1, then I cannot choose vertex number 2. Similarly here, if I choose vertex number 3, I cannot choose vertex number 4, vertex number 6. But if I choose vertex number 4, I cannot choose vertex number 3 only. So that means here also the vertex number 4, if I choose vertex number 4, then I cannot choose only one vertex. So it means I still have other vertices. It's possible I can take 6 also. So it's better to choose 4 among 3 and 4. So that's our strategy. So you have to think about all those vertices whose choice will discard minimum number of vertices. So that means if you here if you choose 3, then you cannot choose 4, you cannot choose 6. But if you choose 4, you cannot choose 3, but you can choose 6, right? So here only one vertex is being discarded. So it's better to choose 4 instead of choosing 3. So now again, let's compare all other vertices. So here also, if I choose 6 vertex number 6, I cannot choose 5 and 7. But if I choose 5 also, I cannot choose 9 and 6. So here there are same type of, here we are discarding 2 vertices only. If you choose 6 also, you can discard 2 vertex. But see, if you choose 9, and then you can choose 6 too. You cannot choose 5, but you can choose 6 too. So it's better to choose 9. Okay, so I am choosing 9 to form my independent set. So far, every vertex are non-adjacent. 1 is not related to 4, 4 is not related to 9 by and direct edge. Okay, now let's see what are those vertices which we cannot choose. We cannot choose 2, we cannot choose 3. We have chosen 9, so we cannot choose 5. Now there are only 3 vertices are remaining. So if I choose vertex number 7, I cannot choose vertex number 6, vertex number 8 too. So it's better not to choose vertex number 7. Instead of vertex number 7, let's choose vertex number 6 and vertex number 8 both. Right? So we can choose vertex number 6 and vertex number 8. So now in this set, if you try to insert one more element or one more vertex, so here what are the vertices which are missing? 2 is missing. So if you enter 2, then this won't form an independent set. If you enter 3, then this won't form an independent. So that means this is a maximum independent set. And how many vertices are there? There are 5 vertices in our maximum independent set. So this number 5 is actually important to us, right? So we want to find what is the largest, how many vertices we can insert in our independent set, or what will be the maximum number of vertices we can take to form an independent set. Okay, fine. Is there any doubt in independent set? Someone raised the hand, I guess.
Ma'am, what is the need of independent set?
What is the need of independent set? See, in lecture, I think we discuss independent set with an example that we want to create a program, and in that program there are so many dance groups, so there is some restriction, right? So in several scenarios, independent set can occur. If you, I think in your practice assignment and activity assignments also, there are some descriptive questions which can be solved by independent set. So now it's your job to find out which question related to which concept. There are some questions, they won't explicitly ask you to find out the maximum number of independent set. They will give you some scenario and they will ask you to find out something. And now you have to relate what is this something related to. Either it can be related to vertex cover, independent set, matching, or color. Okay, or none of them above. It's also possible that it's just a intuitive question type of thing. Okay.
Thank you, ma'am.
Yeah, one possible use case that I could immediately think of is graph coloring problem that we have. There we cannot color the same nodes which are connected. So essentially, just a example that came out of my mind.
Yeah, coloring also we take care of the things that 2 vertices should not get the same color. So in that also we can proceed in this way too. But there we have to assign one color, so it will be little bit changed.
Here it is changing.
Yeah, here I think it's changing. If I use the maximum color.
Maximum color is here too.
Okay, yeah. So yeah, we can take the same example. So is the independent set concept is clear?
But color equal to independent set, that is not clear, ma'am. That is contradicting.
Yeah, that's not true. That's not true. That's what he asking. I haven't.
Clear, ma'am. Thank you, ma'am.
Ma'am, will the coloring concept is ahead or not? Will you explain the coloring concept?
Yeah, I'll explain the coloring concept. Just give me a second. I'll connect my phone. So now let's go to the matching. And after that, we'll go to the coloring. Graph color.
Excuse me, ma'am, can you please repeat the concept independent?
See, independent set is nothing but a subset of vertices in which you have to take care of one thing, which is every vertex should be non-adjacent to every other vertex. So that means every vertex should not be connected via a single edge to every other vertex. For example, here, so here in this set, you observe that 1 and 4 is not connected to each other via a single edge. 1 and 9 is also not connected to each other via a single edge, and 1 and 6 and 1 and 8 is also not connected to each other via a single edge. Similar thing is happening for every pair of vertices. If you consider any pair, then that pair is not connected via a single edge. So that's the main thing of independent set. And our task is to find out the maximum number of independent set.
Shortly, ma'am, just like cardinality A or B, the both are same.
Cardinality of A means?
Suppose A and B and both are independent. A intersection of B. Just like
I'm not
imaging.
getting your question.
Ma'am, he's saying intersection of A, if we take another independent set, that should not be matching the intersection should be 0. He's telling an empty set should be.
No, it's not
Is
the
he
case.
right?
Because see, here we have choice. In place of, we can remove one vertex too, right? So if you remove 9 and make another independent set, that will be your independent set, but it will have lesser element. So suppose this is your I1, and if you take I2 to be equal to 1, 4, 6, 8, and this is also an independent set, and if you take the intersection here, then we have 4 elements. So intersection is not empty for any two independent set. If that's your question.
Ma'am, single one is also independent?
Yes, single one is also independent set.
Okay.
So now let's go to matching. So what is a matching? So here's the Dipanshu.
Yeah, I am saying the in independent set, the member in set vertex, if it is connected to through single edge or it is covering
It should not
maximum
connect it
vertexes.
to, yeah, it should not connect it via a single edge. That's the restriction we are following. Okay.
Okay, ma'am. Thank you.
So now if you guys have any doubt, you can raise your hand and I'll take the doubts at the end of the concept. Okay. I think that will be much better. So let's go to matching. So what is a matching? So now overall we have taken independent set vertex cover. Both of them are subset of vertices, but matching is a subset of edge set. So it is a subset of edge, subset of the edge set E, in such a way that two edges should not share the same endpoints, right? So in such a way that any pair of edges should not share any common endpoint. Okay. So in matching, we have to consider all those edges which are not sharing a common endpoint. So for example, if you have a graph in such a way, here are two edges, right? So here is the edge 1 E1, here is the edge E2. So these two edges are actually sharing one common endpoint, which is this vertex. Okay. So in a matching, we cannot take both of the edges together. Either we have to consider E1 or we have to consider E2. So if such kind of scenario happen, then in a matching, we cannot take both of them. But here, if such a kind of thing is given, so here we have three edges, E1, E2, E3, right? So here also, obviously, in a matching, we cannot take E1 and E2 because they are sharing one common endpoint. We cannot take E2 and E3 together because they are also sharing one endpoint. We can take E1 and E3, right? So if you consider E1 and E3, then this will be suppose this is your graph G, and these are the three edges we have, and if you form a subset of edges considering the edge E1 and E3, then this subset will form a matching, right? Then this subset will form a matching. Why it form a matching? Because here any pair of edges is not sharing any common endpoint. Here there is only one pair, and that pair is E1 comma E3, and E1 comma E3 is not sharing any common endpoints. So such kind of subset is known to be a matching. So again, as an independent set, we know if we take a single element, so suppose you take just only one edge E1, then this set is also a matching. And this set is also a matching. Why it is also a matching? Because again, for matching, we just need two conditions. First condition, it should be a subset of H set. Another condition is any pair of edges should not share any common endpoints, right? So here it is a subset of H set, and it is not sharing any common endpoint because there is no pair. It's just a one element. So this condition will redundant. I mean, it's not applicable here, right? So this is a trivial kind of matching. So again, we have an existence of matching, but now our goal is to find out the maximum number of edges we can use to form a matching. So that's our question, that what is the maximum number of edges? What is the maximum number of edges we can take to form a matching? Take to form a matching. Right? So this is the question we need to answer. So for that, again, we don't have any particular method. We just have to go via our intuition. So let's consider the same graph. Let's consider this graph only. And here, let's try to find out what is the matching here. So again, as I said, matching is a subset of edges. It's not a subset of vertices. So it means we have to name the edges so that we can make a subset. So suppose this is the E1. What was there? E1, E2, E3, E4, E5, E6, E7, and E8. So there are 8 edges. So in these 8 edges, we have to consider that subset of edges which do not share a common endpoint and should be the largest subset. So that means you cannot form any larger subset of edges than this which satisfy the same condition. Okay. So let's try to find out a maximal matching here. Okay. Such kind of matching is known to be a maximal matching. Okay, so now let's consider some of the edges. So which edges we can consider? So if you consider E1 edge, then you cannot consider E2 edge because they are sharing a common endpoint which is equal to 2. So, and if you consider E2 edge, you cannot consider E3 and E4 edge because again they are sharing the endpoint. So that means consideration of E2 will not be a good choice for us, because if you consider E2, you cannot take E3 and E4, and we want to take as many edges as we want a maximum number of right, we want a maximum set. So for that we need maximum number of elements. So if you take E2, you cannot take E3 and E4. So it's better to take E1 instead of E2. So if you take E1, then only thing which or only edge which we have to discard is E2. So now we cannot take E2. Similarly, if you take E3 or E4, so suppose you take E3. So if you take E3, you cannot take E4. But if you take E4, you cannot take E3, you cannot take E7, and you cannot take E5. So the good choice will be E3. Right? So if you take E3, then you cannot take E4. Now let's go to the next edge. So the next edge is either you can take E7, you can take E5, you can take E6. Here, if you take E5, then you cannot take E6 and you cannot take E7. So it's better to take E6, because if you take E6, you cannot take E5. So we just discarding one edge. Okay, so let's take it E6. So if we take E6, we cannot take E5. But now there are only 2 edges remain, which is E7 and E8. So we can take one of them only, because if you take E7, then we cannot take E8, and if you take E8, we cannot take E7. So that means here there is only one choice. So let's take it E7. So that means we can take these 4 edges, which again form a subset of edge set, and here these edges, in these edges, any pair of edges if you take, then those edges are not sharing any common endpoint, right? Because if you take pair E1 comma E3, then there is no common endpoint of E1 and E3. What are the endpoints of E1? So endpoints of E1 are 1 and 2, because it's an edge from 1 to 2, connecting vertex number 1 to vertex number 2. Okay, and what is E3? So E3 is an edge which is connecting the vertex number 4 and vertex number 3. So here these 2 edges are not sharing any common endpoint. So that means this pair is okay. Similarly, you can check that any pair is not sharing any common endpoint. So such kind of a subset is known to be a matching. And here we cannot. So here what is the maximum number of edges we can consider? So the answer is 4. We can take 4 edges to form a matching, because we cannot take more than that because of the restriction here. Okay, so this is the matching. Yes, is there any doubt?
Ma'am, if we take E5 in place of E6, there would not be any change in the answer, right? There would also be.
Because
four
in place
elements
of
only.
E6, correct. If you take E5, then E6 and E7 will be discarded, but still we can take E8. So the number of edges will be
E8
same.
can be taken. Yeah.
Right.
Okay, ma'am.
Okay, is there any other doubt related to matching? Now there is one specific kind of matching which is known to be a perfect matching. So in perfect matching, what is the case? So in that matching, firstly, it should be a matching, right? And for matching, we have two constraints. It should be a subset of edge set, and any pair of edges should not share any common endpoint. So this is the condition for matching. So what is a perfect matching? So a perfect matching is, firstly, it's a matching. And secondly, it will cover every vertex. So by covering every vertex means every vertex should be endpoint of at least one of the edge in given matching, in our considered matching, right? So that means it should cover every vertex. That is known to be a perfect matching. And it's not easy to find out a perfect matching. And secondly, it's the case that there are graphs in which there is no perfect matching. So if you consider a graph with 5 vertex in which every vertex is connected to every other vertex, so it's just an example for you. So in that graph, you cannot find a perfect matching. So again, I'll repeat what is a perfect matching. So it should be a matching, and secondly, it should cover all the vertices. Covering all the vertices means every vertex in a graph should be an endpoint to at least one of the edge in our considered matching. Okay, so that's the meaning of perfect matching. And it's not the case that in any graph, it's not always the case that we can find out a perfect matching. There are some graphs in which there does not exist any perfect matching. For example, if you take a graph of five vertices in which every vertex is connected to every other vertex, in that graph you cannot find a perfect matching. That's a homework for you. You can consider. Okay. So a matching is a subset of vertices in which a subset of edges in which every pair of edges should not share a common endpoint. Okay. So yes, sir.
Madam, I saw one of the previous year questions. There is a two families and one family having 4 boys and another family having 4 girls, and they are matching. Their matching is there. How many best matches we can do? So it's
Okay.
so we can solve this problem through this method.
Right. Yeah, it's a question of matching. Because
Yeah.
there also you can make a pair, because I think there is some common relation there. So suppose something like this. So these two vertices are related by one vertex. So I think there is one constant that you cannot match such kind of pair.
Yeah,
So that's a question.
that problem I just pasted in the chat box, madam. So can you see? So you can use a similar way to solve this problem. Can you give us some guidelines?
Yeah, sure. So two family have decided to enter into alliance by marriage. So the first family has okay. So the graph represent the arranged marriage is given below. Either their own age or someone position in it. Yeah, this is a question of matching. Here you just have to
How
find out maximum number of matching eggs.
uh, is it possible to give some clues for how we can start actually this?
Okay, so let's start with some vertex, because obviously we don't have any particular method. So you can start with S1, right?
Okay.
Right, and from S1, if you want to make a pair, okay, so here what you have to do for every edge there are two pairs, right? So for every edge there is one endpoint is some SI and another endpoint is some DI. So what do you do? Just name name all the edges. So that means if an edge connect to S1 D1, name that edge to be equal to E1. If an edge connect to S1 D2, name that edge to be E2, and so on, right? And considering those edges, now find out the matching. So now if you find out the matching, there for every matching there will be two pairs, right? What I want to say. So suppose this is S1 is there. So whatever edges are there, consider E1, E2. So now in a matching, if you consider E1, obviously you cannot consider E2. Right? So in this way, find out the matching and that will give you the answer. Find out the maximum matching. So you have to first name all the edges accordingly and then find out the maximal matching. And whatever the maximum matching will be there, that will give you all the pairs which we can take. Is that fine, Arun?
Yeah. Yeah, madam. Okay.
Yes, Manish.
Ma'am, in the above example, is it perfect matching example?
I don't think so because here we have some intersection points. So let's see. This is one matching we are taking. So if you consider vertex number 2, so in a matching, we can take E1 or E2, right? So if you want to consider a matching, so either we can take E1 and E2. So for covering vertex number 2, we have to consider one of them. So I think it's not a perfect matching here. Because for perfect matching, we have to consider all the edges. Okay, see, we can judge by this. This is our maximal matching, correct? Max matching. We cannot find out matching with more than edges, more than these edges. And if you consider here, then how many vertices we can cover using these 4 edges? So if we have 4 edges, then maximum number of vertices we can cover is 8. Right? Because for every vertex we have two, for every edge we have 2 vertices. We can cover 2 vertices. And in this graph, there are 9 vertices. Right? So that means in this graph, there is no perfect matching. Is that clear? Manish, is that okay for you, this explanation? Because see,
Yes,
the
ma'am.
maximal matching is having 8 edges. So obviously
Yes,
we can
ma'am.
cover 8
I got it,
vertices.
ma'am. So this is not an example of perfect matching.
Yeah.
Ma'am,
So,
you could you please repeat the statement where you said 5 vertices are each, like, could you just complete that sentence once again?
yeah. So see, here this is a maximal matching. So that means here we are considering 4 edges. So 4 edges can cover 8 vertices because for every edge we have 2 vertices. But in our graph we have 9 number of vertices. So obviously we need another edge. So if you consider another edge, then that edge will cover 2 vertices. And those 2 vertices, among those 2 vertices, one vertex will be one of the endpoint of these edges. Because obviously 9, we have 8 plus 1. Right? So for this plus 1, if we take any edge, then that edge will take one more vertex, and then that one more vertex will come from this 8 vertices. So in this example, we don't have any perfect match.
Ma'am, any
Yes, sir.
particular example of perfect matching?
Yeah, there are examples of perfect matching.
Ma'am, for 5 matching, we can draw a line and put vertices on them.
Sorry,
Ma'am,
what?
if we draw a line and put vertices on them, then we can find, I think, 5 matching with no vertex left. Vertex.
I don't think so because see, if you draw a line and then put a vertex, yeah, that's okay. It's up to you, whatever method you want to apply. But I don't think in this case. So what are the edges you are using or considering
Ma'am,
a
I
matching
think
with 5?
1, 2, 3, 4, 5, 6, 7, 8, 9. 9, ma'am.
Oh, number of edges. Which edges you are considering? E1, E2, E4.
E1, E3, E5, E7,
If you
E9.
consider E5, then you cannot consider E7
Ma'am, why?
because they are sharing one endpoint.
No, ma'am, in not that graph. Ma'am, in my graph, it's a straight line.
So, yeah, obviously, yeah. If whatever example you are consider, in that case you can do.
Excuse me, ma'am.
Ma'am, but you
Yes,
said
ma'am.
that if we have 5 matching, then we can't pair.
But you are
we
considering the different graph now. Here I am
okay,
talking
ma'am.
about this particular graph.
Okay, ma'am. I think you have said for every graph.
It depends upon the graph.
Okay.
Yes, Gaurav.
Ma'am, the question Arun has put forward, the son and daughter one, isn't that a perfect match?
That thing I am not sure. I have to look. Yes.
Because as if we match as if we take edge S1 D1 S2 D2 S3, so all the vertices
If you
will be
consider,
covered.
if you take, if you are finding such a matching which is covering all the vertices, so yeah, it is possible to find a perfect matching here, because we can just take the straight lines,
And
whatever
the
is there
solution for
connecting to
that
S1 to D1.
question will be 4, right? Can you please
Huh.
look at that?
Madam, I checked that one. Answer is 5, but
Okay.
we can able to make four only, right? So
Yeah, it's coming 4.
Yeah, because if it is a matching, then obviously at max we can cover 4 vertices. Let me see this question.
Arun, are you sure it was 5?
yeah, it's 5.
Yeah, it should be 4, because in a matching, if you are taking 5 edges, then those 5 edges are taking 10 vertices. So we need 10 different vertices, but here we just have 8 different vertices. So I don't think there is possible matching with 5 edges.
That is not possible because there are total
That is
8
not possible.
vertices. So in 5 there must be one common.
One common vertex, and that is not the case with the matching.
Okay, let's move on ahead.
Yeah, we can discuss it later. And now let's go to coloring. So what is a graph coloring? So graph coloring means here the process is we want to assign one color to each vertices, but there is one restriction, and the restriction is you cannot assign the same color to any adjacent vertices. So that means if two vertices are connected by an edge, then you cannot give the same color to these two vertices. For example, here A and B are two vertices and they are connected by an edge. So if you assign a red color here, you cannot assign red color to the vertex number B, because if you remove this restriction, then there is no point of coloring. So graph coloring means you have to color a graph. Coloring a graph means coloring the vertices. So we have to associate a color to each vertices in such a way that if two vertices are adjacent to each other, they should take a different colors. Okay, so now here the question will become, okay, so we can use the same number of colors as the same number of vertices. So that means for each vertex, if we assign the distinct color, then this is a one possible coloring. So here the question will become, what is the minimum number of color we need to color a graph? Okay, so this minimum number of color is what we want to find. So what is
4.
It depends on the graph. So if it's a planar graph, then the answer is 4. But if it's not a planar graph, then we need more than 4 colors,
Please repeat
or less
this.
than
I
4
can't.
colors.
Ma'am, please repeat this. My network is
Yeah,
slow.
sure. So see, what is a graph coloring? So graph coloring means we have to color vertices, right? So we have to associate a color to each of the vertex, but in such a way that if two vertices are adjacent, then they cannot take the same color. And
What is the adjacent means?
Adjacent means they should connected by an edge. Adjacent neighbor connected by a single edge. For example, A and B are adjacent to each other. Adjacent means the term adjacent should reflect, right, something like neighbor or
Both
connected
side
to by
point.
some edge. Right.
Ma'am, both side point. Yeah, vertical.
Sorry, what?
Ma'am, both side vertices.
Both side vertices, yeah. So whatever vertices are connected to each other, those vertices are adjacent vertex. So if you take red color to this vertex number A, you cannot take red color to vertex number B and vertex number C. This is the restriction we are applying when we are coloring a graph.
Madam, we can say this way also, right? So says one edge connecting two vertices. Then it will be adjacent.
Yeah, right. So if Yeah, that's the thing. So if two vertices are connected by an edge, those vertices are known to be an adjacent vertices.
Yeah. Okay.
Adjacent vertices or neighbor vertices, whatever thing you want to say. You can say. But adjacent is the standard term which used in graph theory. That's why I'm saying.
Ma'am, is a planar graph and a non-planar graph? I don't understand.
Yeah, so I'll repeat. So in planar graph, so first let's recall the coloring itself. So coloring means you have to assign a color to every vertex in such a way that if two vertices are adjacent or connected by an edge, they should get a different color. That's the thing we want. Now our question is to find out the minimum number of color we can use to color a graph. Because obviously maximum number we have. So if you assign every vertex a different color, that will be one possible coloring of a graph. So we want minimum number of colors to color a graph. So for that, again, we have some of the methods, but that's a little advanced method. So here we just have to go via our intuition. Okay. So there is one theorem that's known to be a four-color theorem for planar graph. So if you have a planar graph, then for any planar graph, you just need four colors to color that graph. Okay. So what is a planar graph? So a planar graph means planar graph. So a planar graph means a graph which you can draw in such a way that there is no intersection of two edges at any point. So that means, for example, this graph, if you consider, then here you can say, okay, these two edges are intersecting, but this graph we can draw in a different way. So for example, if I draw this graph in this way, right? So now here what is happening, there is no intersection of, or there is no cross section of any two edges. So such kind of graph is known to be a planar graph. So if we can draw a graph in such a way that there is no intersection of edges, those graphs are known to be a planar graph. And there is a four color theorem which says that any planar graph can be colored by minimum number of by four colors, right? So we need at least four colors to color a planar graph. Okay, but it's a kind of difficult to find out a planar graph if the graph is very complex. Okay, so in a simpler way, you can take the to be a planar graph. But see here also the four is the you can say that we need at most four colors. So for example, if you consider this graph, right? So now in this graph, how many colors do we need to color this graph? And this is a planar graph, right? No edges are intersecting. 1, 2, 3, 4, 6. How many colors do we need?
Ma'am, I think this
So
cannot be happen. All are
yeah, so
connected.
let's see.
6.
Ma'am, two colors.
Yes.
Ma'am,
All
two
have
colors.
different colors.
Two colors.
All will have
Right.
different
Ma'am,
colors.
two colors.
Okay, fine. So let's see. So suppose I'll assign red color to the vertex number 1. So I cannot assign red color to any of the vertex. So that means I have to choose another color. So suppose I'll assign golden color to vertex number 2. Now I can assign golden color to every vertex because these vertices are not adjacent to each other. So that means here we need two colors. Although it's a planar graph, because planar
Why,
graph
ma'am,
means the edges
both
should
are
not intersect.
golden color?
Because these vertices are not connected by a single edge, right? There is no edge which is connecting to all these vertices. They are connected to one, but they are not connected
But
to each other
this is
via a single
different
edge.
color, no? 3 suppose is a blue color.
No, but we need minimum number of colors. So why do we need another color
Okay,
if we can color them by
just a maximum number color.
minimum number of colors we need. We don't need maximum number of colors because maximum number of colors is obviously a number of vertices. You will give a different color to each vertex. That will be your one type of color. We need minimum
the
number of
answer-
color to color a graph.
So
Okay, suppose
ma'am,
that
so the answer is 2, na?
Yeah, so the answer
So,
is
ma'am, if the edges connected all the vertices, then there
then
would
the
be
answer will
different
change.
colors for each.
Yeah, then the answer will change. So let's try that also. So suppose all the edges, all the vertices are now connected by edges. The outer vertex is also connected by edges. Now the answer will be different. Okay, so now let's try. So again, I'll assign red color to vertex number 1. Okay, so here I am assigning red color. Now if I assign golden color here, I cannot assign golden color to this vertex, this vertex, but I can assign golden color to one of these vertices, right? So I can assign golden color here. Again, I cannot assign golden color to this vertex. I cannot assign red color to this vertex. So now here I have to choose another color, right? So you have to wait that situation where you have to choose. So that means the condition is okay, I need to choose another color. So suppose I'll choose some other color to color this vertex. Suppose I'll choose violet. So I cannot choose this. So I cannot color this particular vertex via the same color, because obviously they are connected via a single edge. Okay. So here I can choose violet color because it is not connected via a single edge. So again I have to choose one more color. So suppose I'll choose green. So then I'll choose green. So now the question, now the answer will be different, right? 4. So my motive is to say that don't just blindly apply the planar graph theorem. So okay, this is the planar graph. So just say the answer is 4. No, there are planar graphs which required minimum number of less than 4 number of colors to color those graphs. Okay.
Madam, I don't understand.
But ma'am, this is
planar graph?
4 is the maximum.
Wait, one by one. Yes, sir.
What is planar
Okay,
graph?
ma'am.
So I don't understand what the.
Hello, ma'am.
See, planar graph means just 1 second. Okay. So planar graph means a graph is given to you. So suppose this is a graph is given to you. Here you are saying, here we can say that, okay, there is one intersection of edges. But this graph you can redraw, right? This is a one type of drawing we can make. We want to just connect to vertices by an edge. So it's not necessary to connect via a straight line. We can take a loop. So if you consider this graph in this way, now there is no intersection of edges.
Okay.
So planar graph means no matter how differently you draw a graph, there should be one intersection. So if this is there should not be any intersection.
Every joint have a vertex, na ma'am.
Understood, but this concept is very well.
Yeah, so it's not in our syllabus too. It's just an introduction of planar graph. Planar graph is a very vast topic.
But which application this method we are using, madam? Actually, this one, the coloring.
Coloring is used for, there are so many real life applications. There are some questions in your practice assignment also. So for example, if you want to set up some electronic circuit in some, if you want to connect some cities via some roads, right? So there you can use this coloring to find out which minimum number of roads we can just take and connect, right? Or there are so many problems you can find out easily.
Okay.
Ma'am, but here these are not planar graphs, right, ma'am? You just write minimum of 2. So
no, these are planar graphs. So planar graph 4 graph theorem says that you need at most 4 colors. It won't say exactly 4 colors. It says at most 4 colors.
Ma'am, but you said na ma'am, wood shouldn't intersect, ma'am. But
here it's not intersecting, na. Here there is one vertex is there. This is a vertex. Intersection means this is one vertex, this is another vertex, this is one vertex, this is another, and then this intersection is happening. Here there is no vertex in this intersection. This is going to be end. Although we can draw this graph in this way, so it's not.
Ma'am, one vertex is not graph, I think.
One vertex is not graph.
Yes, ma'am.
What? No. One vertex is a graph. Is a graph.
Vertex
It is a graph. Even though if I say now the screen is blank, it is also a graph. Because there is no vertex, there is no edge, but still it is a graph. And this graph is known to be a null graph. Yeah.
Null graph.
So, yeah, that's a null graph. There is no vertex, no edges, blank. That's a null graph. Okay. So someone pasted a. What is the minimum? So
yes, ma'am. Can you teach me that question, please?
So it's a very famous graph. It's known to be Petersen's graph, I guess. This graph, the star one.
It's like pyramid.
It need 3 colors, if I am not wrong. 3 color to color this graph.
Ma'am, can you teach me how to update that, please?
Yeah, sure. So this is our question. We need to find out what is the minimum number of colors. Here we need to color this graph. Okay, so this is known to be a Peterson's graph. It's a very famous example. So let's try to find out. So suppose I'll give. So you have to start with any vertex. So you can choose any vertex and start with that. Yes, Satvik, is there any problem?
Ma'am, 3 colors.
3 colors. Yeah, I know. It needs just 3 colors. So let's try to understand why. So suppose I'll give red color to vertex number 5. Now there are three vertices which are adjacent to or which are connected via single edge from vertex number 5, and those are 9, 0 and 6. So I cannot give red color to 9, 0 and 6, but I can give red color to vertex number 4. Now if I given red color to vertex number 4, I cannot give red color to vertex number 9, I cannot give red color to vertex number 1, cannot give red color to vertex number 2, but I can give red color to vertex number 3. Okay, so now I can take red color to vertex number 3, but if I taken red color to vertex number 3, I cannot take to vertex number 8, I cannot take to vertex number 7, and all those vertices. Now any vertex cannot be colored using red color, because if you take any vertex, that will be adjacent to one of these vertices. 0 is adjacent, or 0 is related to 5 and 3. 1 is related to 4, 6 is related to 5. 7 is not related. So yeah, so we can take red color to 7 too. Okay, because 7 is not related to 3, not related to 4, not related to 5. So we can take 7 and we can give a red color to vertex number 7 too. So 8, we cannot take red color to vertex number 8, right? Because of the same reason. It is connected to 3. So we cannot take the red color here. We cannot take the red color to 9 too. Now we have to use another color. We cannot use red color again and again now. So now let's take green color. So suppose I'll color the vertex number 6 with green color. Now again, vertex number 1, for vertex number 1, I cannot use red color, I cannot use green color. Vertex number 0, I can use green color because it is not adjacent to vertex number 6. There is no direct edge. For vertex number 2 also, I cannot use red color and cannot use green color because 2 is connected to 0 and we are given green color to vertex number 0. And 2 is connected to vertex number 7. So that's why we cannot give red color to vertex number 2. So now we have to take, but we can color vertex number 8 with green color because it is not related to 0 or 6. Correct. So green color we can use here. Again, for 9 also we cannot use green. Yeah.
Ma'am, can we color 9 also with green?
Yeah, ma'am, with green color. Without using 8.
No, we can't.
That's also fine. It's up to you.
Yeah, okay.
We can choose. So we can take green color to vertex number 9 also. But again, now we have to take another color because we cannot use the red again and we cannot use green again. So let's take another color and color the remaining vertices. Okay, so that means we need 3 colors. This is a very famous graph. It's known to be a Petersen's graph. So this graph has so many nice properties. Okay, so that's not our concern. So here we need at least 3 colors to color this graph.
Thank you, ma'am. Thank you so much for the explanation.
Yeah. So you have to proceed in this way only because we don't have any fixed method.
Ma'am, you said
Yes,
some
Manish.
intersection is there. We should not color. We have to use different color. Could you once repeat that statement?
Intersection.
Between 0 and 3, there is an intersection of 4, right? Previously, you said we should not use.
Okay.
We have to use different colors.
I have said this one that for 0, I cannot use red and violet color, right? I have to take. So I think I have said for 1. Yes. So for 1, we cannot use the red color. We cannot use the 6 color because it is connected to both of the vertices. It is connected to vertices with colored with red color. It is connected to the vertices colored with the green color. So I have to take another color here. So I think that's the.
Okay, ma'am. Okay, understood.
Okay. So for coloring, you just have to go with this method or whatever comfortable to you. But
Ma'am, 0 is connected to 2 and 2 is
sorry.
violet.
Here then it should be
green.
green.
Yeah.
Initially I was right. Fine.
Excuse me, ma'am.
Yes, Sanskriti.
What is the maximum number of colors I can choose?
You can
The
choose
number of vertices.
you can choose the number of vertices. That's a one thing. But see, it doesn't matter. So suppose here there are 10 vertices because we started from 0. So there are 10 vertices in this graph. If I choose 20 colors and I don't use 10 colors, then still I can say that okay, using these 20 colors I can color my graph. I mean this question that what is the maximum
colors?
number of colors we need?
Ma'am,
See,
how 20?
I mean you choose a set and from that set don't use some of the colors. You just whatever color you need, use them and say that using this set also we can color. Because okay, so let's forget about this. So at max
So
you
then
need
answer
the
could
number
be
of
infinity.
vertices colors.
Hello,
Yeah,
ma'am.
so that's
Then
the thing why
answer
I'm
could
saying.
be infinity, na? I have taken all the color present in the word
Or
and
the
I'm
colors.
using few.
Right.
And I'm using the few.
Right. So that's why we need minimum number of colors. Because again, if you guys remember, then coloring is nothing but a function, right? A function from vertex set to a set of colors. Now here the set of color depend on my choice. Whatever set I need, I can take. Because also we know that this if a function is there, then this is a domain, this is a codomain. So for codomain, there is no restriction. So you can choose whatever set you want. So that's why the question will reduce to the minimum number of color. That what will be the minimum number of color we need to color them. Okay. Fine.
Okay, ma'am. Thank you.
Ma'am, in the previous question that Arun has put forward, there are we only calculated number of edges in a perfect match, and I think question is asking number of possible arrangements, and the condition given in the question is either you can marry a
The
person
same one or
with same
the
age or one step above or one step below. The only way the 5 is coming up if like if S1 marries with D1 in a correspondence set like perfect match, or if S1 marries to D2 and S3 to S4 like diagonally in both ways. And fourth arrangement would be if S1 marries to D1 and S2 marries to D3 and S3 marries to D4. Similarly, from downwards, if S4 to D4 and S3 to D2, and see. One perfect match would be S1 to D1, S2 to this. This is a perfect match.
perfect match is kind of obvious here because we can take the straight lines.
Then other would be other
perfect match.
arrangement would be S1 to D2 and
S1 to D2,
S2 to D3, S3 to
and
D4.
S3 to D.
This is second arrangement. Now similarly, diagonally take all diagonal edges from downwards.
Those are there.
This is the third arrangement. Fourth arrangement would be if S1 marries to D1 and S2 to D3 and S3 to D4. Like one straight and two diagonals.
Okay, so here we want to consider all type of matchings, I guess. So how many
I
matchings are
think
there?
this is what the question is asking. This is the only way 5 can come up the answer. Because in
there are 5
end-term
type of
exam, IITM wouldn't make a mistake if the solution was given 5.
Two families have decided to enter into.
Because this seems like a very promising question. It
Sir,
would
Gaurav sir, this one, this two for straight line and a diagonal 3, I can able to identify. Another two, how you calculated?
Arun, one is like perfect match. Take the second is like take diagonals from like S1 to D2, S2 to D3, and S3 to D4. Or similarly, from downward to upwards, like S4 to D3, S3 to D2, and S2 to D1.
Okay, so yeah. So here we have, it's not actually related to matching. Here you just have to find out what are the possible number of ways we can arrange this. So one thing is clear, we can take S1 to D1 and all those things similarly, right? So this is will be one. The second is the diagonally, right? That means S1 to D2, S2 to D3, and S3 to D4. And then S4 to D3, right?
Yeah, right.
So that means
Ma'am,
second
why
one
can't
will be
we take D3 to S4?
D3 to S4.
Yeah, that's the same
We
thing.
have
You
taken
can
that.
take
We have
S4 to
taken
D3
that.
or D3 to S4. Both things are same.
Okay.
As
So
9,
this
I mean,
question
directions are there.
is a simple matching, right?
Yeah, it's not
Does
simple
it
match. It's not related to matching.
incorporate perfect matching?
Correct.
Okay.
So here we just have to find out how many ways we can match these elements, right? So yeah, because
Seems
S1
like a
cannot match to
question of
D3, S1 can
combination.
match to D2 only.
So what, ma'am? Total 3, no?
5 arrangements.
This question.
5 arrangements will be there.
Excuse me, ma'am.
Yeah.
Ma'am, it will be the perfect matching if we consider all the pairs. For example, if we are considering S1 matches with D1, then we can matches S2 to
Yeah,
D3
correct,
and
correct,
S2
correct,
to
correct.
D2, and means cross,
Right.
one cross, and remaining are horizontal lines.
Right. Because see, in every position, what we are saying, each of SI should be matched to some DI, and both are different. I mean, if S1 is matched to D2, then we cannot match S2 to D2. Right? We cannot take this into the same pair because we have
But
to
we
find
can
out
do S1. But we can do S1 to D1 with S1 to D2.
S1 to S1 to D2 we can do, and S2 to D1 we can do. This
One
one we
person
can do,
can
and this
only
one we can
marry
do.
a single person. That's what the question has given the condition.
Uh-huh.
Improper.
Either S1 D1 or either S1 D2.
Yeah.
Ma'am, in that case, there are 5 perfect matches.
Possible, right? 5 perfect matches.
5 perfect matches are there.
Perfect match is only one. S1
No,
D1.
no, 5.
No,
There
5
are
will
5.
be there.
There are 5.
Because any matching you are considered, you have to take 2 pairs, right? And these
Ma'am,
2
you
pairs will be
said
distinct.
a perfect match should cover all the vertices.
Yeah, it will cover all the vertices, right? Because you are saying that every person is married. I mean, every SI is getting connected to every DI. So one is this. If you take diagonally 2, there will be always one matching. There is
Diagonally,
this one.
2 people will be missing out. If we take diagonal, S1, D4 will miss out, or either D1 or S4 will miss out. If we take diagonals.
Yeah, in diagonally, you can think of S1 matches with D2 and S2 matches with D1. Okay.
Then
so first
who will
4
D1
are get
D1
matched.
will match with?
Sorry?
Okay. Just wait.
Who will
Let's
D1 match with?
wait. So let's try with first thing. Okay, the first one is this one. Correct. So one is correct. Let's go to the second one. So second one is diagonal.
Yeah, D1
Now,
and
what
S2
about
are
S4 now?
missing out.
No, ma'am.
S4 D1.
Ma'am, please consider S1
S4
to
D1
D2.
can.
No, ma'am, no.
No. That's the restriction now here.
Yes, ma'am.
Someone or one position younger or older. So that means S1 is not connected to D2. So we cannot take the direct. So this is not a perfect matching, but this can be one kind of arrangement we can make.
So the perfect match is only one, right?
It's not one.
Ma'am, only one. S1 D1.
Only
S1
one, right?
S3.
Yeah. It will be
In
one
all
because
the
we
other
don't
arrangements,
have
someone will
cross
miss out.
conditions.
Man, but
One
it
will be
is
missing.
possible, right? S1 to D2 and D1 to S2.
No, actually, see here this condition is given that they each one must marry someone either their own age. Either their own age means they should be a same level, or someone one position younger. So that means either S1 can marry. Suppose we are at S2, so S2 can marry D2, or it can marry D1, or it can marry D3. It cannot marry D4. So that's why when we are at S4, we can take D4 or D3 only.
Yeah, that I got, ma'am.
Yeah,
And
I
just
got what you are saying. You are right.
consider S1 to D2 and S2 to D1.
And
The
S3
first
to
cross.
D4 and D3 to S4.
And S2 to D1.
S2 to D1.
Yeah.
Okay.
See me in same fashion, S3 to
S3
D4.
to D4 and D3 to S4.
Yeah.
S3
This
to
is a
D4
perfect
and
match also.
S4 to D3. Correct.
Yeah,
This
ma'am.
is
So,
also a perfect match.
Yeah, ma'am.
Now
So
the
in this
answer
case,
is not
we will
5.
get 5 matches.
Okay.
Yeah. So if you are considering S2 to D3.
Because here one cross we are
D2.
taking above and below. We can take one cross here and then consider the straight lines.
Yes, exactly, ma'am. Exactly.
Oh, right.
And one more thing, one more is possible. One cross, first cross, and remaining
First
two are
cross and all the straights are
straight lines. Yeah.
Yeah.
But sorry, but how the 5 counts are there? I'm not able to understand actually. 5 counts how?
Yeah,
now you can now you can get. See, the first one will be the straight one.
Right. Okay.
Now the second one will be one cross and all other
One
things
cross
are
above, one cross above,
one cross above.
below.
Okay. Second.
This is one possibility. Second one.
Okay.
Now this will be the third one. Right, one cross below.
Oh, understood. Okay. I got it.
In this way we can get it.
Got it.
Yeah, this is this question. I mean, I'm also seeing it first time. I don't know about this question.
Okay. Thank you, Sweta.
So the answer is 5 perfect matches.
5 perfect matches.
Ma'am, will you explain what Madhav pasted in the chat box? You have to give to your friends.
And no two nearby should get same.
Array,
Then use coloring for it.
It's not the question.
It's not the question, it's just an example he's giving for uses of coloring. Where this color
Application
concept
of
is
Okay,
used.
thank you.
coloring.
Fine, let's move to another concept. Yeah, it's a good
Excuse me,
question
ma'am.
although.
Excuse me, ma'am. Before
Yes,
that,
Shweta.
I came across one question in which I am not able to decide which way to go. Just a minute. Yeah,
Put it in
so
the chat box, we can discuss.
ma'am, I am joining from my mobile and question
It's
is
okay, you can just verbally say.
okay. So its question is like that. The organizer decided to model the graph where the nodes are the session and ages represents pair of sessions with overlapping timings.
Okay, fine.
So now we have to make arrangement that each session should be conducted in a separate hall.
Correct.
So minimum
It's a
number of
coloring
halls.
question.
Yeah,
it's a coloring question.
Answer is coloring question, but I fail to understand why we cannot use independent set.
Independent set, why you cannot use? So suppose these are the 3 sessions. Independent set means if 2 vertices are not adjacent, then we have to take. I think you can use independent set to here, but there is the problem. So independent set, we have to take the maximum independent set, right? So
Hello, ma'am. What is the question actually?
the question
Ma'am,
is, there are some
I have a
courses.
similar question.
Yeah.
I have a similar question I have put in chat. Oh, sorry.
Can you please repeat the question?
So the question is, we have to form a schedule in such a way that there should not be any overlapping. So obviously this we can solve by coloring.
Ma'am, by
So
coloring method, sir has given the example in the lecture of this only.
Right. We can solve it by coloring method. But I think we cannot solve it by independent set. There is a thing happen with independent set is...
This question I could not solve because I do not know why. They are saying that they're connected by different these edges, they mean this different
slots will be there. So that means if
slots.
maths and English is connected by an edge, so that means maths and English are holding in such a slot that there is a clashes of sorts. So that means if maths starts from 9 to 10, then English start from at least 9:30 to 10:30. There is some clashes. So we cannot put maths class and English class in the same room, correct?
Yes.
Because the maths class is from 9 to 10, it's from 9:30 to 10:30. So we have to take 2 separate rooms so that we can hold these classes. So now the question is, what is the minimum number of rooms we need?
Yes, the answers they have given, it is in the book, but the answer did not match. They said arts, maths, history and science and English. That is how they said it.
Arts, maths, means? Okay, see. So I think the independent set, what has happened? We have to consider the vertices, right? So we have to consider the vertices which are non-adjacent to each other. So I think we can solve this by independent set too. Because see, if we have some subjects which are overlapping, then obviously they cannot be in our independent set. So yeah, we can solve this also by independent set. So is the answer is incorrect by independent set, Shweta?
Yes, ma'am. Answer is only find the minimal coloring. Minimal coloring.
But have you tried to find the maximal independent set there?
When they are just idea of which way to go, which method should we select. They didn't mention the graph or exact timings or dependency of vertices or edges. They just
No, we can select. Yeah, right. We can take independent set because see, what is a maximal independent set means we have to consider all those vertices which are not adjacent to each other, right? And if these vertices are not adjacent to each, yeah, sorry, we cannot solve it by independent set. I bet we cannot solve it. I'll give you one example.
Please explain the next concept, ma'am. So many times.
Yeah. It's okay. We can, I'll extend a little bit up to 11 maybe. So see, consider this graph because it's important to understand. You guys can do the questions, right? So suppose this is my graph. Here we have some vertices. Suppose this is 1, 2, 3, 4, 5. And suppose the same condition are here, that vertices are the subjects are there, and if there is an edge, then there is some clashes of type. And we want to find out what is the minimum number of classrooms we need to run this program. Okay. So now here, if you consider the independent set, then what will be your maximal independent set? 4, obviously, right? You can take 2, 3,
It's
4,
2,
and
3,
5.
4, 5.
Right.
Yes,
So
ma'am.
this is
But we
our
need 2
independent set.
classrooms.
But we just need 2 classrooms. We
2
can take one
classroom
classroom
for
for
one
course
and
number 1 and another classrooms for all the 3 courses. So that's why independent set won't give us the answer. Is that clear to you, Swati?
Yes, ma'am. Yeah.
So, is there any doubt in this question? We just have to find out the coloring. The graph is also easy. Okay. Now let's go to the next.
Ma'am, excuse me.
Yeah.
Ma'am, the subject question in which math and in which it says edge represents a conflict between two classes that cannot be scheduled in the same time slot. And in the solution, they have put math and history in the same time slot. But math and history have an edge. They are
So that
different
means,
colors, but they do have an edge.
so here how they considering the graph? So each class is set of time slots in which it can be scheduled, and each time slot has a maximum number of classes that can be held during the time slot. So we can represent this by a graph. So what is represent the classes? And each edge represent a conflict between 2 classes that cannot be scheduled in the same time slot. Yeah, so maths and history cannot be scheduled in the.
But they have put math and history in the time slot 1, and English and science in time slot 2. But English and science do share an edge. It means they have a conflict. Only maths and arts can be put in one time slot.
Yeah, because here this is not a coloring question, right? Because here red color is there, red color is there. They are connected by
Because coloring concept is not making any sense here, because art and English do have an edge, but they have same color, and math and science are of same color, but they have an edge. So coloring is off.
Coloring is not the answer here.
So still the answer should be like 4 time slots. Math and arts can be put in one first time slot. Then all the 3 subjects should have a
another time
slot of their own.
Yeah, this is not a right answer here. Whatever the given is here, it's not a correct answer.
Yeah, it may be right.
It's not a coloring also, because green is there, red is there.
Right.
I'll look into this question.
Okay,
Also not
thank you.
clearly stated what is. Okay. So yeah, don't worry about the time. I mean, we have to cover major, important topics. I won't go in detail of each algorithm, so that's the case. So let's go to the next topic. So which is so I'll jump to the BFS and DFS process now. So there is only 2 things I want to explain, that how we can construct a BFS or DFS tree from a given graph. And the second thing is how we can judge that 2 edges given a BFS tree or DFS tree, how we can judge a 2 edges are 2 vertices is connected by an edge in a original graph or not. Okay. So for that I'll consider this particular graph only. Okay, so this is our graph is here. So in this graph, let's try to find out what is a BFS tree and what is a DFS tree. Okay, so I hope you guys are familiar with the BFS and DFS process, how these 2 processes work. So let's go with the BFS first. So BFS says select one vertex and then go to its neighbor and then explore its neighbors step by step. So that means first you have to explore all the neighbor of the first source vertex and then go to their neighbors and explore all the neighbors of neighbors and then go to the next step. That's how BFS works. So let's start BFS process from vertex number 5. Okay. So if I again, so what is a BFS tree? So BFS tree means you have to consider all those edges which are using which we used in BFS process for reaching from one vertex to another vertex. So we have to select all those edges and form a tree. So let's start with the vertex number 5. So if we start with vertex number 5, the BFS process says you have to explore all the neighbors of vertex number 5. So what are the neighbors of vertex number 5? Vertex number 9, 0 and 6 are the neighbors. So this is vertex number 9 is a neighbor, vertex number 0 is a neighbor, and vertex number 6 is a neighbor. So now these are the 3 neighbors of vertex number 5. Now BFS process says now explore its neighbor's neighbor. So now we will explore first 9's neighbor, then 0's neighbor, and then 6's neighbor, and then go to the next level. Okay, so what are the neighbor of 9? So the vertex number 9 has neighbor 4, 5 and 8, but 5 is already listed in our BFS process, so we'll leave it. We'll go to 4 and 8. So the neighbor of 9 is 4 and 8. Okay, now what are the neighbors of 0? So the neighbors of 0 is 3 and 2. Again, 5 is also a neighbor, but it already been listed, that's why we are leaving it. The neighbor of 6 is 1 and 7. Right. So now we are done with all the neighbors because if you go to vertex number 4, then vertex number 4 will have neighbor 9, 5 and 2. But 9, 5 and 2 has already been listed. And although if you calculate the number of vertices here, so there will be 1 vertex, 3 vertex, that will be 4 vertex. And again, we have 6 vertex. So ultimately 6 plus 3 plus 1, which is equal to 10. So it means this is our BFS tree. So we have listed all the vertices. So that's how we can calculate if a given tree is a BFS tree or not. Now here you observe. So suppose if someone asks you, so this is a smaller tree, but the question can be that is there an edge? Is there an edge between vertex number 5 to vertex number 1? Okay. So what will be your answer? So suppose the graph is not given to you, only BFS tree is given to you, and this is the question that you have to find out: is there an edge in original graph from vertex number 5 to 1? So what will be your answer?
Yes.
Why it will be a, so suppose, okay, so let's see, suppose I'll say that, okay, in my original graph, so suppose, then what I'll do, I'll say that the graph which represent this BFS tree is nothing but this graph. I'll take the
So
same
ma'am,
graph.
hello ma'am, it is asking for a direct or indirect.
Directed. Is there is a direct edge from
Then no
vertex
ma'am,
number?
no ma'am, there is no.
No, ma'am. There is no.
No, there is no edge. Okay, so
If it
this is
asks
an
about
easy
path,
case.
it may be.
Correct. So this is an easy case, but in some cases, suppose you have different, because it's kind of
How do
obvious.
you conclude that this edge will not be there?
Yeah, I'll explain. So see, so what you have to do is, if such kind of question is there, and if you are having confusion, what you'll do, just take the same BFS tree and make an edge between these two vertices. So I'll taking the same BFS tree. So I'll take the vertex number 4 here, I'll take the vertex number 8 here, vertex number 3 here, vertex number 2 here, vertex number 1 here, vertex number 7 here. And the question says there is an edge between vertex number 5 to 1. Now this is the graph I am considering. So suppose this is my original graph. Now in this graph, you apply a BFS process and find out what is the tree you are getting. If you are getting the same tree, then this edge could be there. If you are getting the different tree, then this edge is not there in the original graph. So that's the process, that's a verified process. Sorry, what?
Now, what is difference between them? They are same.
Now see, if you apply BFS process here, what will happen? If you start with vertex number 5, BFS says list out all the vertex, all the neighbors of this vertex number 5. Now what are the neighbors? Neighbors are 9, 0, 1 and 6. That means 1 will be here now. 9, 0, 1 and 6. Now we have to explore the neighbors. So the neighbor of 9 will be 4 and 8. The neighbors of 0 will be 3 and 2. the neighbors of 1, now see BFS tree will change, but the neighbor of 1 is only 6 and 5, which are already listed. So here the neighbor of 6 is 7. Now this BFS tree and the original given BFS tree is different.
Yes.
Are you getting my point? Which are what I want to say. So that means if such kind of thing happens, so that means this edge won't be there in our graph. That's a well-proved technique to find out if an edge is there in a BFS tree or not. Just take a BFS tree, make an edge, and again apply the BFS process over there. If you are getting a different BFS tree, that means this edge should not be there. And if you are getting the same BFS tree, this edge will be there. Okay.
And I will start from the same vertex, that is 5. Means
Yeah, you have to start with the same vertex.
Ma'am,
The starting
you're
vertex is already mentioned.
you're proving that
Yes,
it
ma'am.
is wrong, then it will become the original one is BFS. Is it right?
Hello, ma'am. Please repeat it once more.
Yeah, sure. Yeah, Manish, what you're saying, that's right, because it's not a BFS tree which is given to us. So obviously, if there is an edge, then BFS tree will be different.
Okay, ma'am.
Also, there is one rule which says that, so see here what is happening, this vertex number 5 is of level number 0, right? So here you can assign level to each of the pair of vertices. These vertices are level number 1, these vertices are level number 2. So in BFS tree, there won't happen, in the original graph, there will be no edge from a vertex jump, a vertex which situated at level number 0 to level number 2. So that means such kind of edges won't be there in any graph. If a BFS tree is given to you, and if they are saying is there an edge from vertex number 5 to vertex number 1, then observe that vertex number 5 is of 0 level, vertex number 1 is of level number 2. So there is one jump between levels. So from 0 you are going to 2. So such kind of edges won't be there in any graph. But this will be a little bit complicated when it's come to the neighboring edges. So suppose some type, this method will work most of the times. But sometimes you have to go with the lengthy one, and this is the lengthy one that you have to consider. So a BFS tree is given to you. Whatever edge is there, consider that edge in your tree and assume that this is your graph now. And in this graph, on this graph, apply the BFS process. If you will get the same tree, then that edge could be there, then the answer will be true. So yes, this edge could be there. But if you are getting the different tree, then this edge won't be there. Okay, and this is a foolproof method. So here you cannot, you won't get any different answer.
So, ma'am, we have to make a BFS of a BFS tree.
Correct. By just entering one edge. Whatever option is there, just enters.
We have to let that there exist a edge between those two vertices and then make a BFS.
Correct. Make a contradiction.
Ma'am, then which jump is allowed and which jump is not allowed? 0 to 1 is allowed or 0 to 2
0 to 2, so 0 to 1 may be allowed. I cannot guarantee it, but 0 to 1 may be allowed, but 0 to 2 is not allowed.
And
jump of a level is not allowed.
Okay.
2 to 0 is also not allowed. So from 1 to 3 is not allowed also. So suppose there is one more set of vertices are there. So there will be 1 to 3 levels. So 1 to 3 is also not allowed. So one level jump is not allowed. It's 18 to 90% case that such edges won't be there in the graph. If 0 to 2 is there, then it won't be in the graph. 1 to 3 is there, then it won't be in the graph.
Okay.
So the basic reason is this.
If we ask then if they are in edge in between 4 and 8, so how
That's
do we find?
Correct. That will be fine.
Yes.
Because see, if you consider the same tree with the edge in 4 and 8, then still we get the same BFS tree. That's true. So in between level, there could be an edges. But in the jump of one level, there won't be an edges.
Then how, ma'am, 5 and
But in original graph, there is no edge between 4 and 8.
But this BFS tree can be related to some other graph in which we have the edges. So forget about that graph. This BFS tree can be related to more than one graphs.
So you mean to say that one edge below, one edge above, or same level, we can have the edges and not others.
Right. But the jump off and level, we cannot have the edges.
It is for BFS, right? Not for DFS.
It is for BFS. No, not for DFS. DFS work very randomly. There you just have to guess by your intuition that the edges are there or not. So for example, so is this question is clear? So you can judge now which edges can be there in the graph and which edges cannot be there in the graph. One thing is, just go by your intuition. You know BFS process, right? So if that's it,
Ma'am, will
if
you
this
please,
level thing is there, then obviously you can answer. But if this level thing is not there, this is the method you have to do.
ma'am, will you please summarize this? I am not.
This method is a lengthy one, the BFS tree again. So this level process is easier, but it works all the
Right.
time.
Can you please
Yeah, it
please
works
the
80 to 90%. There
can you
will be
take the
little
example of
confusion.
4 to 8 in the
Sorry,
next
what?
explanation? Can you take the explanation of 4 to 8? Will there be an
4
edge
to
to
8.
4 to 8
Okay.
Ma'am,
using
please
the lengthy
summarize it
process?
without interruption, ma'am.
Fine. So suppose this is your BFS chain. So suppose this is your BFS tree now, and the question is there an edge 4,8 in the original graph? Right? This is your question. So what will you do? So first thing is, you can say that, okay, these vertices are of same level. So one explanation is, method number 1 is, so since 4 and 8 are in same level, so it can, so we can say that there can be an edge. So there can be an edge. So if the vertices are of same level, you can directly say that there can be an edge. Okay. The method number 2 is, so what you will do, you'll just make a graph. So you'll make a graph with in such a way that with BFS tree plus that edge. Okay. So this is our BFS tree.
We can draw graph itself.
Yeah. So I'll take a graph with BFS tree with this particular edge, right? 4 and 8. 4 and 8 is what they have asked, right? And now assume this is your graph, and now apply the BFS process here. So now if you apply the BFS process, so BFS process start with, the starting vertex will be same. So you'll start with 5. It says that explore the neighbors of 5. So the neighbors of 5s are 9, 0, and 6. Correct. Now explore the neighbors of neighbors. So the neighbors of 9s are 4 and 8. Right? Neighbors of 0 is 3 and 2. And neighbors of 6 is 1 and 7. So now whatever BFST we have got, it is same as the original one. Right? So this is the original one for us. I mean the given BFST.
Now, if suppose we are asked, is there an edge between 4 and 3 or 2 and 1? What can
That's
I do?
also okay. So if there is an edge between 4 and 3, yeah, that's also fine. Because if there is an edge between 4 and 3, that's also fine. Because we are exploring the neighbor of 9. Neighbors of 9 are 4 and 8. So 4 and 8 will be there. We are exploring the neighbor of 0. So neighbor of 0 is there. 3 and 2 will be there. That means this edge is not considered. That's why I'm saying that if the vertices are of same level, there can be an edge. If the vertices are one level intersection, that means if the vertex is at level number 1 and then level number 2. So in this case also there could be a possibility of an edge. But if the vertices are one level jumped, so that means 0 to 2 or 1 to 3 or 2 to 4 type of thing, then there may not be an edge. Okay.
Ma'am, 9, 3 is not edge, but 9, 0 is edge.
Correct. 9 and 3 is not an edge. Because if 9 and 3 is an edge, then the BFS tree will look different. That's why I'm saying.
Okay, got it.
Okay. Yeah, just do a little bit practice, you will get it seems to be lengthy method here, but once you understand, it's just a matter of 2 minutes, right? You just have to make a tree. It's easy.
Simple.
Right. Fine. So now let's go to the next concept, which is DFS process is okay to you guys. Is that fine?
Yeah.
Is there any doubt in DFS?
Yes, ma'am. Yes, ma'am.
Yes, only this, if they again ask edges in a DFS tree. That is a tough.
They just same method you have to apply in DFS also. I don't think they will ask in DFS because DFS method is very random. There we don't have level structure, we don't have such kind of thing. So it's a very tough thing to judge an edge is there in DFS or not. Not that tough, but obviously it will be little bit trickier. There is no method. So here, as I told you that this is the method you can follow, right? It's a value-proof method. This method will work. But in DFS, since we have choices, right? So what does DFS says? So suppose I'll show you one graph. DFS. How randomly it works. So see, so suppose this is a graph and I want to find out the DFS tree for this particular graph. Okay, so what can I say? I'll start with 5. So I'll start with 5, I'll go to 9, right? It's my choice. I can go to any neighbor. DFS says just go to any of the neighbor. So I'll go to 9, then I'll go to 8, then I'll go to 7, then I'll go to 6, and then I'll go to 1, then I'll go to 4, I'll go to 2, then at 2 I got stuck, right? So 5 to 9 to 8 to 7 to
Ma'am,
6 to 1.
0.
Zero.
2 to 0.
0, right. 4 to 2, 2 to 0, and 0 to 3. Yeah, 2 to 0 and 0 to 3. Now this is the DFS tree.
Oh my God.
It's a very random thing. So
Ma'am,
that's
DF
the
process. Hello.
Yes.
Yeah, DFS process. First tours and the second is suspend and the third is
right. That's a lengthy version of DFS. So intuitively, what is we are doing? We just have to choose a vertex, suspend that vertex, and explore its neighbors. But there we have choices. That from 5, I can go to 9, I can go to 0, I can go to 6. It's my choice. I can go to any vertex. Now here, what has happened? That it's very. So suppose someone asks you, is there an edge from 9 to 7 in the original graph or not? So it's kind of tricky to say because maybe there is an edge, but the person who made this DFS tree did not choose that edge to form the DFS tree. Correct? You're getting my point? What I want to say, that such kind of question cannot be.
Yes.
It does not make sense that much in DFS tree as it
Yes.
makes sense in BFS tree.
Okay, got it, ma'am. So DFS won't be asked. Thank you.
Yeah, 90% chances it won't be us. 10% depend on our luck.
Left them.
Ma'am, don't you
Fine.
make the question paper?
No, I guess.
Ma'am,
No, I
ma'am, a
guess.
quick question.
Sorry, what?
Ma'am, a quick question. So
Yes.
there was some concepts regarding forward edge, back edge, cross edge. Those are all related to DFS only. Those can also be considered with the
Yeah.
BFS as well.
Those are related to DFS numbering. So first you have to do DFS numbering, and then we have some results. Based on those results, we have to judge is that a forward edge, back edge, or cross edge.
Okay, thanks.
It's actually a lengthy process. I mean, it's not that important topic. They haven't asked it for so many times, I guess. Forward edge,
Okay.
back edge, cross edge.
But the gist is like first I have to create a DFS and then only I have to decide whether there is a forward, backward, or a cross edge, correct?
Correct. First you have to consider the DFS. Okay, so now let's go to the next topic, which is the spanning tree, and then Prince and Kruskal. These are the important topics I have. So let's go to the spanning tree. Those adjacency matrix question you guys can solve, right? Just make a graph from given adjacency matrix and then answer the question. And that way you cannot, it won't be confusing.
Yes, ma'am, that is.
Yeah. So what is a spanning tree? So in a graph, so first of all, what is a tree? So tree is nothing but an acyclic connected graph. So a connected graph in which there is no cycle. So it also known as a minimally connected graph. So that means if you remove one edge, it will got disconnected. And if you add one edge, it will be connected graph. So a tree is a cyclic connected graph. Now what is a spanning tree? So in a given graph, we have to find out a tree which cover all the vertices. So that means, for example, if I consider this graph, Right? So suppose this is my graph with some vertices 1, 2, 3, 4. So in this graph, I have to find out a tree which uses these 4 vertices. That will be our spanning tree, right? So spanning tree means it should uses the same number of vertices present in the graph, and it should be a tree. Tree means connected and acyclic. So here one type of spanning tree is this.
So what is
So I can take
acyclic?
what acyclic connected graph.
Okay.
Connected means you can reach from one vertex to any other vertex. There is a
Any
path
other?
between any two vertex. Yeah, any vertex. Now here consider this one G1. So now this is a tree because obviously it is connected. We can go from one vertex to any other vertex. We can go from 3 to 2 via 1. We can go from 3 to 4 via again 1. So that means it's a connected graph and it's an acyclic graph. There is no cycle here. So it's a tree. And more or less it's a tree and it is using all the vertices present in the graph. So such kind of tree is known to be a spanning tree.
Where we can go one dot to another dot is spanning tree.
Yeah, so it's a spanning tree. That means it is covering all the vertices given in the graph. So this is one kind of spanning tree. But you can consider another kind of spanning tree with the same graph. So suppose this is our tree. This is 1, 4, 3, 2, right? So this is another graph G2. This is also a spanning tree. Correct? Because it is a tree. Again, it's a acyclic connected graph. And it's a spanning tree because it is covering all the vertices given in the graph. So for a graph, there could exist more than one spanning trees. Okay, so we have to judge is the tree is given is a spanning tree of the graph or not. So in that case, what you have to judge? So suppose the question asked,
Ma'am,
or suppose you want to judge a spanning tree for a given graph. So first requirement is it should be a tree. Second requirement is it should connect all the vertices, and the third thing is it should use the same edges whatever present in the graph. So for example, here there is no edge from vertex number. Okay, so here all vertices are connected to each other. So if I consider this graph, 1, 2, 3, 4, and if I'll say that this tree, one, two, three, four. Whereas this is a tree, yeah, obviously it's a tree because it's connected acyclic. It is also using the vertices, using all the vertices, but it is using some edges which is not there in the tree. Okay, there is no edge from 1 to 3. So it is not a spanning tree for this graph. Okay, not a spanning tree.
So how did you
Numbering
connect that
different,
1
man.
with 3?
Yeah, it's just an option. So suppose some graph is given to you and someone says that is this a spanning tree for this graph or not? So you'll say no because there is no edge from 1 to 3 in our original graph. So you cannot say that this is a spanning tree for this particular graph.
Okay, ma'am.
excuse me, ma'am.
Yes. Yes, Gaurav.
Ma'am, is it always true to say that a spanning tree of a graph will have same number of vertices and edges one less than as of the
Yeah,
graph?
correct. That's true. Because see, a spanning tree
Because,
should cover all the vertices. And for a tree, we know the number of edges is one less.
like, okay, so it's always true.
Yeah, it's always true.
Okay.
Fine. So it's a very, I mean, it's not that tough to judge a tree is a spanning tree for a graph or not. First of all, it should be a tree. It should cover all the vertices. And second thing is the edges should match. So for
And
example,
it
there
should
is
be acyclic.
acyclic,
Okay.
connected and acyclic. Okay. Now
And
let's
for
go
an
to the,
acyclic graph, is it necessary it should be directed?
no. It's not necessary. Directed, undirected graph also can be acyclic.
And can an acyclic graph have a spanning tree?
Yeah, acyclic graph can have spanning tree. Itself, you can take that. That graph itself is a spanning tree for,
Okay,
right?
okay.
So now we have two algorithm again. Yeah. So now we want to find out the minimal cost spanning tree. So what is the cost? So first of all, let's recall what is a weighted graph. So if a graph is given to you, yes, sir.
How to find what are the how many possible spanning tree are available like that for a particular graph? Is there any formula for that? Actually, they asked
Uh,
in practices.
in practice assignment. So I think that graph is very easy. So that's there you just have to judge by yourself. Just make a different type of spanning tree. But in general, I don't think there is a particular formula for trees for spanning trees. For trees, I know some formula is there, n into 2 to the power n minus something like that. But yeah, there is no particular spanning tree. You just have to make a different type of spanning tree using that graph.
Okay, ma'am, thank you.
Now, the one question we have is that what is the minimal cost spanning tree for a given graph? So minimal cost spanning tree means we have to find out a spanning tree whose cost is minimum. So what is the cost? So in that spanning tree, whatever edges you are using, you just have to add all the weights assigned to those edges. So for example, here, this is the one weighted graph. So in this graph, I want to find out what is the minimal cost spanning tree. So for there, I have two methods, Prim's algorithm and Kruskal's algorithm. So Prim's algorithm says you have to select one root, and that root will be the will be the least cost edge, and from that root you have to grow your tree. Okay, so that's a Prim's algorithm. And the Kruskal's algorithm says you will just take all the vertices as your disconnected components, and then attach edges in such a way that the cost of edge is minimum and it won't create a cycle. So I'll discuss these two algorithms using this particular graph. Okay, so let's start with the Prim's algorithm. So Prim's algorithm says choose the least cost edge. So what is the least cost edge here? So this is the least cost edge, correct? This edge has cost 1. So that means I can choose this edge in my Prim's algorithm. So I start with my Prim's algorithm with this particular edge, which is connecting to vertex number 7 and vertex number 6.
Ma'am, what is the least cost?
Least cost means the cost is the smallest one. So here you observe that all cost is there. 11 is the cost of the edge. 7 is the cost of the edge. 6 is the
14.
cost of the edge.
So it will
Similarly.
be given like this in the exam.
Yeah, given like this, or the numbers will be little upward. It's not in between the edges. It will be little upward here.
Okay, okay.
Okay.
Ma'am, is there any easier method to find the least cost? Because we have so many spanning trees we can find in this.
No, this Prim's algorithm, Kruskal's algorithm are very easy methods to find least cost spanning tree. We just need a number, right? We don't need spanning tree. We need a cost. Cost will be a number. Right?
Okay, ma'am.
We just need that minimum number. So here I am choosing this set. So okay. So now we have to grow our tree. So for growing our tree, we have to select all those edges which are connected to this edge, which has minimum cost and it won't create a cycle. That's the general method of Prim's algorithm. Correct. So here we have choices. We can select 8 edge, this edge with weight 8, this edge with weight 7, this edge with weight 6, and this edge with weight 2. So obviously we have to select the minimum one because we need minimal cost spanning tree.
Ma'am, this 6 and 8 are indirectly connected, no?
Sorry, what?
Ma'am, this 6 and 2 and 6 and 2 are indirectly connected.
6 and 2. This
The
is the
6
weight of
cost.
edge.
Yeah, 6. The edge between 8 and 6, which cost 6, is indirectly connected, na? To
Why
7.
indirectly connected?
Ma'am, from 7
See,
it is
we can
connected to
take
6, then 6, 8.
but this edge has 2 endpoints now. So I can take any edges which is connected to either 7 or connected to 6. Any of those edges are in our choices.
Okay.
Okay. So now, what will be our choice? Our choice will be this particular edge. Correct. So this edge with cost 2. So I have add one edge with cost 1. I'll add second edge with cost 2. Now what are the other choices? Now I can take this edge. Again, what we have to choose all those edges which are connected to the required vertices. So that means all those edges connected to vertex number 7, 6 and 5. Okay, so for vertex number 7, those edges are weight of 7, 8, 7, now 6. This one is 4, this one is 14, this one is 8, 10. Again, we have to consider the minimum. So this is the minimum. Okay, so this will have weight 4. Now let's again guess. Now let's again observe what are those edges which are minimum cost and do not create a cycle. Okay. So now we have 10, 14, 2, 6, 7, 11, 8, and 8. These are all choices. Again, select 2, right? Because the addition of this edge in my tree does not create any cycle. Okay. Now, again, what are the choices we have? So we have 14, 10, we have 7 also, we have 6 also, we have 7 also, 11 also, 8 also, 8 also. Now the minimum cost is 6 here, but if you select 6, it will create a cycle in our tree, correct? Because if you made a spanning tree like this, so far we have selected these edges, right? We have selected 1 cost edge, 2 cost edge, and then we go to 5 to 2 with cost 4, then we go to 2 to 8 with cost 2. Okay, now if I select this edge which is connecting 8 to 6, then it will create a cycle. So obviously I cannot take this particular edge. Now what will be the next choice? Next choice will be an edge with cost number
Excuse me,
7.
ma'am. 2 and 5 why connected?
For 2 and 5 are connected by an edge with cost 4.
Okay.
That's
Yeah,
why
yeah.
we take this edge, right? Okay.
Yes, ma'am.
Now, 8 and 6 are connected, but we cannot take this edge because it will create a cycle. We cannot take this edge, again it will create a cycle. Now we
2
can
and
take
3.
this edge, right? 2 and 3. So we'll take 2 and 3 with cost 7. Now if we, and obviously we cannot take, now we have choices 14 we can take, 9 we can take, 10 we can take. So now here I cannot take 14 or 10. I cannot take 14 because obviously it will create a cycle, but I can take 9 and connect the vertex number 4 to vertex number 3. So in such a larger scale graph, you have to connect the vertices. So now observe which are the vertices are not connected yet. Okay, so we have connected all vertices except 1 and 0. So if I want to connect 1, I have one edge from 2 to 1 with cost 8. I have one edge from 7 to 1 with cost 11 and 8, right? So I'll consider this edge, which connect 2 to 1 with cost 8. Now I have to consider 0. So I'll connect 0 with cost 2. So this is the spanning tree which we get by Primson.
Why don't we connect 1 and 2?
We connected 1 and 2.
Oh, I mean,
Y and edge 8.
down here.
Now the cost is just summation of all these numbers.
Hello,
That
ma'am.
will be
Please
the cost.
repeat this algorithm one time.
Yeah, sure. So see, the process is start with the minimum cost edge and then try to append all other edges which will connect our vertices in such a way that we have to select minimum cost edge. In all the choices, among all the choices, we have to select the minimum number. And the next second thing is we should not create a cycle in between. Okay. So I'll repeat. So we started with this particular edge. This will connect 7 and 6. Then we have choices with weight 8, 11, 7, 6, 2, right? So we choose this particular edge with 8 with weight 2, right? Now after selecting this edge, the choices will I mean we have many other choices. So we have 4, we have 14, we have 10. And now among all those numbers, the 4 is the minimum, so that's why we selected this particular edge. Now here, as I selected this edge, I have choices, I have more choices now. So I have the choices to select an edge with weight 2, with weight 8, with weight 7, 14, 6, 7, 11, and 8. And among those numbers, 2 is the smallest one. And if I consider this edge, it won't create a cycle in my tree, correct? So I can consider this one also. So as I consider this one, again, the choices are now as it is. So now the smallest number is 6. But if you consider 6, and if you add this edge in your tree, it will create a cycle. So that's why we cannot consider this particular edge. Now the next possible thing is either considering this edge which connects 7 and 8 with weight 7, or we can consider 2 and 3 with weight 7. So here if you connect 8 and 7, again it will create a cycle, right? If you connect 8 and 7, obviously it will create a cycle. We can start from 8, go to 7, 6, 5, 2 and return back to 8. So it's a cycle. But we are talking about spanning trees, and trees do not have a cycle. So that's why we cannot take this edge. Let's take this edge. We can take this edge. Now, after taking this edge, we have so many choices. So if you want to go by the similar method, the next choice will be 2 to 1 because this edge will have 8 cost, right? The cost is 8 and all other edges will have a bigger cost than this edge, right? Except this one also. So you can take this one too, but let's take it 8. Okay. Now
Or we can
after
take
this,
7 to 0 also.
7 to 0 also we can take. This is also possible. Now, Yeah, we can take 7 to 0 also. But if you take 7 to 0, then the tree will little bit change. Now in the next step, I have to consider this particular edge because this will be a cost 4. And then this will be a cost 9. It depends on the choices, which weight you have to take. Since the weight are same here, so we have two choices. But the weight will be distinct and the spanning tree will be unique. Otherwise, it won't be unique.
Ma'am, so minimum cost spanning tree is not unique to a graph. Matlab.
No, it's not unique. It depends on the choices. If the weight is our same, suppose I'll take if I assign the same weight to every
Can
edge.
you like you are saying 7 to 0 we can take. Can you quickly make a spanning tree if we start from 0?
Yeah, sure. It's if no. See, here the starting point depend on the minimal cost edge. So here the minimal cost edge is of edge number 1. So that's why we have to start from there.
How can we take then 7 and 0?
Sorry, what?
How can we take the edge between 7 and 0?
Okay, so what happened at this stage when we haven't considered any edges at this stage? Okay, so here I have choices of taking edges with weight 8, 11, 8, 14, 9 and 10. So here the minimum number is 8. Now here I have a choice. I can took either 7 to 0 or I can took 1 to 2. Okay, so
But
you can choose any one of them.
Ma'am, if the two edges will have same number, minimum number, such as if one is there for two edges, then which one we should choose?
That's your choice. It does not depend. The cost won't change because the cost is same, right?
First of all, we have to start from minimum and then we continue from that.
Right. That's the algorithm.
The final weight will remain same.
The final weight will remain same.
210 or 701 both comes out to be 12.
Right. The weight will be the same. Weight won't change.
Thank you.
Okay. So this is the Prim's algorithm. Kruskal's algorithm is very easy than Prim's algorithm. There we just have to take care of not making a cycle. Okay. So I'll explain the Kruskal's algorithm from this one.
So, ma'am,
What
in the
does
last graph, hello, ma'am.
Yeah.
Hello, ma'am. In the last graph, you have from the 2, you went from the one side to the 3 and then one side for 1. So, was that allowed? I mean, going backtrack.
Yeah, it's allowed. It's allowed. You have to choose an edge. So you can go back. It's not the issue.
Okay, so we have chosen 3, then 4, then we have it was ended. So we then backtrack to 2, then chose the 1.
Right, right. So it's allowed. It's not an issue. Now, Kruskal's algorithm is, I think, I think it's easy than Prim's algorithm because what does it? Kruskal's algorithm says just list out all the vertices. So list out all the vertices. So 1, 0, 7 is there, 8 is there, 6 is there, 5 is there, 4 is there, right? And 2 and 3, no? 2 is there and 3 is there. Right? So Kruskal's algorithm says list out all the vertices and now append the edges among these vertices with the two restrictions. So the first restriction is choose the minimum cost edge, and the second restriction is do not create a cycle. Okay, that's the only two restriction we need. So what is the minimum cost edge? Again, the one is the minimum cost edge. So first I'll append this one. Okay. Now what will be the another minimum cost edge? So these are the two edges with the minimum cost too. So I can take first this edge and then this edge. Okay. And we have to do this process until and unless all vertices are get connected. Okay.
Yeah.
So that will, I mean, this stopping process will take care by not creating a cycle. Okay. So let's move ahead. So now what will be the next minimum cost here is this 4,
2, 5.
this 4. So we can connect 2 and 5 with 4. Can connect 0 and 1 with 4. Okay. Now after 4, what will the next cost is 6. So, but here observe, if I take this edge, I'll create a cycle in my tree. So that's why we cannot consider this particular edge. Okay. So now this 6 is gone. Now what is the next minimum cost is 7. So this is 7, this is 7. But I take this edge, then again I'll create a cycle in my tree. So obviously we cannot consider this one. So I can take 2 and 3y vertex number, sorry, cost number 7. So after cost 7, what will be the next minimum number is 8, right? So here also you have two choices. So what you can do, I can connect 1 and 2 with an 8 with an edge with weight 8. But now if you connect 0 and 7 with this particular edge, then it will create a cycle, right? We can go from 0 to 7, 7 to 6, 6 to 5, 5 to 2, 2 to 1, 1 to 0. So that's why we cannot take this edge. If you are taking this particular edge from 1 to 2, you can take one of them. You cannot take both simultaneously. Okay. Now here you have choice. So you can choose any one of them. If you select this one, we have to remove this one. If you select this one, you have to remove the other. Okay. So yeah. So now the only 4 is the only vertex which is not connected. So now what will be the minimum cost? So 8 is there, 8 is 1, right? 9 is the minimum
33.
cost now. That's it. This will be your spanning tree because every vertex is got connected and we have uses the minimum cost edges.
Why, ma'am, 6 not connected?
6 is connected now. 7 is 6 is
No, no,
connected.
8 to 6. 8.
Because if you connect this, then it will create a cycle here.
Oh, do not
In
cycle it.
tree, in tree we don't need we don't want a cycle.
In any tree, man.
This is Kruskal algorithm, no?
This is Kruskal's algorithm. It will just say take all the vertices and append the edges in such a way that you should choose a minimum cost edge and should not create a cycle.
Ma'am, but the graph is same in both the situation.
Yeah, it's same because here the weights are in that way. If you choose if there are some choices, so for example in Prim's algorithm we have one choice, right? In Prim's algorithm, yeah, the graph is almost same. In Kruskal's and Prim's algorithm, the graph will be same until until and unless the weights are distinct. So for example here, if I make all the edges with the same weight, then it may happen that Prim's algorithm and Kruskal's algorithm will give different spanning trees. But if the weights are same, then they will give us the same spanning tree.
Ma'am, actually it should be same, right, ma'am, almost, because we are going for minimum cost, right?
Yeah, cost is same. And the tree is almost same because if weights are different, then T is almost same. But if the weights are same, then we have choices in Prim's.
Their motive is same, so figure is same.
Right.
So I mean,
Ma'am,
Kruskal's
what is the
algorithm,
issue
we
with the
make.
cycle?
Okay, you go ahead first.
Yes,
Ma'am,
Laksha.
what is the issue with the cycle? If we make a cycle, then what wrong will
Because we
happen?
want spanning tree. Right? We
Okay.
want to create a tree. A tree means acyclic connected graph.
Okay.
Yes, Gaurav.
So in Kruskal's algorithm, we start with writing all the vertices and appending all the lowest weighing edges.
Correct.
And in Prim's algorithm, we start with the lowest weight edge.
Edge and then grow the tree.
Grow.
And for growing, we need branches, right? So we select all those branches which is connected to the already existing branches.
But
That's the concept.
start with the lowest weight edge.
We have to start with the lowest weight.
Okay, thank you.
Both other situations.
Okay. So yes, Saurav, is there any doubt? Is there
No,
any
ma'am.
doubt so far?
No, ma'am.
Okay.
Ma'am, can you
So
mention all the important topics regarding Entom for week 9 to 12?
9 to 11. We don't have 12 week. 9 to
11.
11.
Actually,
So
question is every concept related.
heavily conceptual related.
Yeah, week 1 to 9.
He said every.
He is asking for 1 to 12, I guess. 1 to 11, I guess.
Yeah, so I'll list out the important topic for 10 to 11 first. Right. So far, whatever I have covered, those are the important topics. That means those 3 vertex cover. Right. Whatever I have covered so far, those are important. Yeah, sorry, what?
Vertex matching.
The Bellman-Ford algorithm.
Bellman-Ford algorithm is a lengthy process, right? So you can think that if there is a 1 hour of question paper, and if I give you only 5 vertices and then say that apply Bellman-Ford algorithm, you have to do it at least 5 times. So it's not a feasible thing to ask a Bellman-Ford algorithm in the question paper, but they can ask some conceptual question from Bellman-Ford algorithm. So for example, what are the restriction? Right?
Ma'am, is the
What are
end
the
of the
restriction
topic?
is
So,
there?
ma'am, in short, can you please explain that?
Okay,
What
yeah,
the
sure.
algorithm is now?
So I'll explain what are the uses of it. Descartes algorithm anyone can ask, right? And Descartes algorithm is also easy. I hope you guys remember the fire and whatever the method we have explained Descartes algorithm, right? So what happened? So the first okay, I'll list out some remarks here. So remarks is for we cannot use Descartes algorithm for negative edges. This is a one remark. The second remark is
Ma'am, what is negative edge?
a negative weight edge means if a graph is a weighted graph, so suppose this is a weighted graph, and here in place of 8 weight, if I have -8 weights, -8 weight as the weight of this particular edge, then it's a negative weight edge. So in
Okay,
place
okay.
of positive weight, we have negative weight.
Yes, ma'am.
A negative weights, right? So we cannot use Descartes algorithm for negative edges. We can use Bellman-Ford algorithm for negative edges.
This one more can ask. That's it.
Right. And these only for single source shortest path problem, right? Single source. Single source means from a fixed vertex, I want to find out the minimum, shortest distance to every other vertex. This is single source shortest path. Okay. And the third thing is for negative cycles. Negative cycle means if you have a cycle whose cost is negative. So if you add all the cost of the edges used in the cycle, then that cost is so if that cost is negative, then that cycle is known to be a negative cycle. Okay. So for a negative cycle, the shortest path problem, shortest path problem is undefined. The reason is
question here that if the cycle is having total cost of 0, can we use Belmont-Ford or we cannot use Belmont-Ford? Suppose
you can use zero is not a negative cost, right? Negative means -1, -2, something like that. Then you can use Bellman-Ford.
And how many iterations? Suppose there are 7 columns, then I will do 0 to 6 or 1 to 7. How many iterations will be there?
Both are same. See, 0 to 6 also you will do 7 iteration. Ultimately, the iteration should be 7.
Okay, 7 columns means 7 iterations, right? 0 to 7.
Right, 0 to 7. So I don't think, see, question on Bellman-Ford is very time taking, in my opinion. So Bellman-Ford, they can ask only a conceptual question on Bellman-Ford algorithm. I'm not saying you should not study this algorithm. It's a very good algorithm, but based on our question pattern or our exam pattern, asking question from Bellman-Ford is only conceptual. Either they can ask you some 1 or 2 distances they can ask. Either the first iteration they can ask, or up to second iteration they can ask. After that, I don't think. Descartes algorithm is kind of easy. You guys are already know. We just have to go one by one and find the distance there. And the third point is for negative cycle, the shortest path problem is undefined. So we cannot use any algorithm. At this point, so many people get confused that if there is negative cycle, then you cannot use any algorithms. Okay, not use any algorithm. And the reason is because the problem is undefined. That's why. So these are the 3 remarks.
Ma'am, can you explain the negative part? It's confusing.
Negative cycle one. So see,
Floyd-Warshall is even more longer than Bellman-Ford, so it won't be asked, I think.
Right, correct. Those are so long algorithms. Floyd-Warshall algorithm, and Warshall's algorithms. Again, they can ask only where it will be used, what are the restriction we need to consider, or what is the conclusion we can draw from that algorithm. That means forward washer algorithm is related to all pair shortest path, right? It will give us the shortest path between every pair or every possible pair of vertices. Okay.
Ma'am, what is
So
the
now,
difference between washer and Floyd washer?
so Floyd actually used the concept of washer. So that means washer derived the transitive closure formula that A plus is equals to B plus C. Right? This is derived by the washers, and the Floyd uses this concept to formulate into an algorithm, and that algorithm is known to be a Floyd washer algorithm. So washer is not an algorithm. Washer just a conclusion or just a result we have given in terms of transitive closure and B plus, and using that thing, Floyd introduces an algorithm that's known to be Floyd washer algorithm. Okay. So negative cycle means, so suppose I have this graph, something like this. Okay, so here the vertices are 6 and the weight is, okay. Now what is the weight of this particular cycle? So here if you consider a cycle from 2 to 3, 3 to 4, 4 to 5 and back to 2, then the weight is -1 plus -3 plus -2 and plus 1, which is -5. Correct? The weight of this particular cycle is nothing but -5. -5. Now, if I want to find out the shortest path from 1 to 6, then what will be the shortest path? Shortest path.
Undefined, because if you want a negative weight, you have to just go around that path.
Correct. Go around that particular cycle. Because one thing I can choose, okay, 1 to 2 and 2 to 6 I'll go. That cost will be 8. But if I move along the cycle, so suppose I'll go to 1 to 2 and then move along this particular cycle and then go back to 6, then the cost is 8 minus 5, which is 3. And if I do this move along the cycle 2 times, the cost will reduce to even further, right? -2. And again -7 and so on. So in this case, there is no negative number or no minimum number we can stick.
And then why
right?
we go around twice, ma'am, for the cycle?
Because we want shortest path, right? Shortest path means minimum weight we want. So we can reduce our weight of this particular path by just going around a cycle.
Ma'am, it can go to minus infinity if it is.
That's why the problem is not defined here.
Okay.
We cannot find out the shortest path if we have a negative cycle. So in this case, you don't, there is no, we cannot use any algorithm.
Is that you written undefined?
Yeah, undefined means.
Yeah, ma'am, not defined.
Yeah.
Now, ma'am, please mention the important topics for 10 and 11.
Yeah, so far, whatever I have covered, those are the important topics. That means, let's have to mention. So you can say that Vertex cover.
Matching.
Independent set. Matching, we can say, but I don't know. Matching is also okay, though. But coloring is obviously important. There is always a one question on coloring. Coloring is the must topic. It's a kind of easy. I don't think you guys need more
Yeah,
time.
ma'am.
Yeah. So coloring, second, and then adjacency matrices, whatever question you already said. Adjacency matrices are there. And after that, yeah, BFS 3. BFS 3. That edges question, right? Edges one question. And after this, so yeah, so after that, this we have a discards algorithm, maybe. It's not that important, but it's easy. You can find out discards algorithm easily. And then spanning tree.
Shortest path problems.
Sorry, what?
Shortest path problems.
Shortest path problems. Yeah, for that only discards algorithm will be there. And yeah, the few remarks you already know, right? Uses of algorithm. Uses and restrictions of algorithms. Those things you should remember, that which algorithm is used in which scenario. Uses and restriction of algorithms. Okay. Now spanning tree and Prim's and Kruskal's algorithm. Those are the important topics from week 10 to 11.
But if in examination there was a graph in which it also have negative weights, then we can't use Kruskal algorithm.
Yeah, we cannot use this class.
Then we have to use the Bellman-Ford algorithm.
That's also you have to check is there any negative cycle or not. If the negative cycle is there, then you cannot use Bellman-Ford too, because the problem is undefined.
Yes, but in
It
grade
is only
assignment they
per
have given
cycle, huh?
negative cycles.
No, they should not use, because if negative cycle is there, the problem is undefined. So you
Yeah.
cannot use Bellman-Ford.
No,
So
I'm
if
not a
that the
negative
case-
cycle, negative weight I'm saying.
If negative weight is there, then you can use Bellman-Ford. That's why
Okay.
we introduce Bellman-Ford for negative weights only. Okay.
Madam, end time exam, the duration is 60 minutes or 90 minutes, madam?
90 minutes, I guess.
Because 3 hours for
For
2
last
subjects.
day term is 90 minutes.
And ma'am, approx number of questions?
Approx number of questions will be by 15 to 17 at max.
Last time it was
Including subparts too.
But
Last time
madam,
it was 10.
but exam now, if then both morning session and afternoon session, both we need to go. How it will be actually?
Actually, that I don't know. I mean, not how the exam process.
So who are
Can someone answer? If someone already taken
You have a break between the two shifts.
No.
It's from 2. The afternoon session will be from 2.
Like first session is from 9 to 12, then 12 to 2 is a break, and 2
Then,
to 5 is
yes.
another session.
I guess
Yes,
there
yes,
was
yes.
a change in the timing, I guess. There was a change in
Yeah,
the timing.
it's on admit card you have seen.
No, admit
There-
card is not
Admit
given.
card
but-
is given or what?
No,
No,
no.
It
it
will
is
be
not
given.
Not admit
It
card,
will be
bro.
given. It
Just
is
like
not
a
given
seal.
yet.
But they have informed that the timing will change
So
for the center.
who are having 4 subjects, then it's their life is miserable actually.
Exactly.
Not for 3
Don't
also
say
it is
that.
Yeah,
miserable.
it is actually miserable. Manage
Excuse me, ma'am.
It is. It is hard to manage.
Hello. Can you please?
Yeah.
Hello.
Yes, Gaurav. Who's this?
Today's session is end, you know.
Yeah. That's all from my side. If you guys want to discuss any other topic, we can extend the session for half an hour.
Ma'am, you
Ma'am,
Ma'am, can you please send the PDF?
One by one. Yes,
Ma'am,
Lakshya.
Ma'am, PDF.
Yeah, I'll upload the PDF into the calendar.
Okay.
I'll upload after the session.
Ma'am, will you discuss practice assignment and grade assignment doubts?
Yeah, we can discuss. Of which week?
Week 11, ma'am. Week 11.
Okay, yeah.
Ma'am, should I send the pictures or you
Yeah,
will
just
open?
send the images. That will be much better.
Okay.
Ma'am, can we pass through 10 and 11 as it is 50% mentioned?
50%. 50% is not the case.
Where did you see
40%
50%?
will be there.
Ma'am, 50% from which week?
9
Not
to
50,
12,
you can
9 to
say.
11, I
None
guess.
of the week will have
9 to 11, it's
50%.
50%. 9 to 11, it's 50%.
9 to 11 is 50%.
Yeah, I think so. 40 to
Yes.
50%.
And ma'am, revision of week 9 and 10, is that been covered?
I think there is another session. Someone says that there is a session tomorrow.
Yeah, ma'am, it's written in
for-
calendar. It's tomorrow.
Excuse me, ma'am.
Yes, sir.
Yeah, ma'am. Could you please comment on something about the sum of degrees and number of edges and number of vertices, that kind of formula? Because I have seen 2 to 3 questions are from such kind of formulas.
Okay. So
Yes,
there
ma'am.
is
In the
one
mock
famous.
test also they gave some like M is even degree and N is odd degree. Find the number of edges. Like
All those questions actually related to handshaking level. So this is one of the basic lemma which says that So this is the question which says that if you sum the degree of vertices in an undirected graph, so I'll be precise, in an undirected graph,
And this
so
lemma, what is that?
this is just terminology. They use this theorem, lemma, proposition, results. All those means that it is a one well-known result. Okay, it's
Because
just
he
a
was
name of.
professor is using lemma long time.
Yeah, so we can speak about. So so it says that if we have an undirected graph, then in that undirected graph, the sum of the degree of all vertices is actually equal to twice the number of edges. So this is the formula that if you sum the degree of all vertices V, where V is any vertex, then this is nothing but twice the number of edges. This is known to be an edge equivalent. The reason behind this is very simple. So suppose you have an edge, then that edge will contribute to 2 in this sum. Because if this is an edge E, it will give 1 degree to this vertex A, it will give 1 degree to vertex number B. That means one edge is corresponding to 2 in this particular sum. It is adding 2 plus in this sum. So that's why the sum of the degree is nothing but twice the number of edges. So you can answer such kind of question that in a graph there will be even number of odd vertices, right? So this is one of the common question asked. So suppose we know the things that if you add two odd numbers, we'll get an even number, right? That means odd plus odd is actually even. Even number plus even number is also even, but odd number plus even number is an odd number, right? So here what we have sum of the degree is an even number, right? Sum of the degree is twice the number of edges, and this twice says that it's an even number. So that means if you have odd degree vertices, so odd degree vertices, so if you have odd degree vertices, then they should come in the pair, right? They should come in a pair, so that those pair will form odd plus odd will become even. So this is the reason they say that in a graph, odd number of vertices, odd degree vertices are even. So sorry, the number of odd degree vertices is even.
No, it's like positive, negative markings.
No. There won't be any negative marking.
No, ma'am. I said that even odd is like plus minus, as like we add them.
Plus minus, or you can say odd. See, odd number is what? Odd number means some even number plus 1. So suppose
Yes.
3 is there. So what is 3? 2 plus 1. 7 is there. What 7? 6 plus 1. So here
Yes,
this
ma'am.
plus 1 so if you take two odd number, there will be two plus 1s. So even plus even is even. So these 2 plus 1 will again become even.
Yeah, ma'am. That's what I am saying.
Excuse me, ma'am.
Yes.
Hello.
Yes.
Can you please this PDF in chat box link?
Okay, I'll paste at the end. I'll paste in the chat box also. I'll upload it on the calendar also.
Okay. Calendar
Yes.
calendar uploaded.
Yeah, I'll upload it
Calendar
at
is
the end.
What's bro?
Where you
no,
have the
I
session now?
just
Yes. Okay, ma'am. Thank you.
thank you, ma'am, for today.
Madam, this what you
Hello,
explained,
ma'am.
now,
Hello.
so which topic it's coming, madam? Actually, I'm not seen this one actually earlier. Odd,
11th
even,
class.
degree, and all.
Yeah, so it's just a one remark given by the professor. He just said this handshaking lemma, but actually this handshaking lemma is very important. So it's an easy one. Just say that sum of the degree of all vertices nothing but twice the number of edges, right? So from that we can derive this conclusion. It's a very common conclusion. So it says that the number of odd degree vertices are even.
Ma'am,
What does this mean? I mean, odd degree vertices are even.
So see, for example, if we have a graph G, and in that graph I have 5 vertices. So suppose I have 6 vertices. Suppose I have. So in those vertices, there will be a degree of each vertex, right? So suppose the vertex number 1 has some degree 3, vertex number 2 has some degree 5, vertex number 3, some degree will be there.
Degree means what? It's in degree or out degree? What is that actually?
No, I'm talking about undirected graph. So here the degree means only the number of edges associated to that particular vertex.
Okay, number of edges associated. Okay.
Because of the undirected graph. There is a directed graph version of this particular lemma, which says in degree plus out degree is actually twice the number of edges. Okay. So in that case, among these 6 vertices, if there are odd number of odd degree vertices, suppose 1 and 3 are odd degree vertices, then they will come in a pair. So that means there will be either 2 odd degree vertices. Odd degree means the degree should be an odd number, or 4 odd degree vertices, or the 6 will be odd degree vertices. That's the reason. There won't be only 1 odd degree vertex or 3 odd degree vertex or 5 odd degree vertex. They will always come in a
Now
pair.
got it. Yes, ma'am, understood.
Okay. Yeah. Yes, Vicky, is there any doubt?
Ma'am, I've shared you the pictures. A few questions from practice assignment and graded assessment.
Ma'am, can you explain the independent set again?
Yeah, just wait a
Ma'am,
second.
one request, ma'am.
Yes.
Ma'am, in our for interim mock test, they gave us some mock test, ma'am. In that, some questions like it is printing mistake, ma'am. It is given some coding way, not given in normal way, ma'am. Misprinted. Can you inform them any?
Yeah,
Yes,
yeah,
yes.
I'll inform them if is
That
there
is
any.
not clear actually. That is what he's trying to say.
It's a old mock. I mean, yeah, I'll inform them to upload it.
Did you receive
Ma'am,
the
but question we can't understand because it is written in some other way.
Okay. Yeah, I'll see the mock because I haven't seen the mock. So
Yes, ma'am.
okay. The fine. This is the question. Find the number of different
No,
ways
ma'am.
of
No.
choosing.
That's another connected question. Could you go second question? I
Yeah.
have posted.
Second.
Could you go, please go up? Because this comes under different question.
This one?
Question. Yeah, you can discuss this one. No.
So let G be a weighted graph and in which the weight of all edges are different. So if we run a shortest path algorithm on G, then we will get a unique shortest path from the starting vertex to every other vertex. So this is true. So why this answer is not true? This first option is correct, right?
No, ma'am. Even I don't feel that's correct.
If let G be a weighted graph and in which the weights of all the edges are different. If we run a shortest path algorithm on G, then we will get a unique shortest path from the starting vertex to every other vertex. The weight is different.
Ma'am, it need not be the shortest path every time, right? If weights are same also, we can make at the sum at the end of.
Are different, they are saying, na?
No problem. If the weights are different also, if we take like if 1 plus 14 is one root and
Okay,
7
got
plus
it.
7 is another root.
Right. Fine.
Sorry, 7 plus 8 is another root.
Right. So suppose this is 0, this is 1, this is 2, and this is 4, this is 5. Yeah, so we can have 5 plus 5 or 6 plus 4, something like this.
Yes, ma'am.
Or
My
5,
doubt is why is
7 is.
B not the right answer?
Okay, so suppose G is equals to E comma is a weighted graph where P is this. Let P be the shortest path from Vi to Vj. If we increase the weight of each edge in the graph by 1, then P will still be shortest path from Vi to Vj. So I think that's if we increase The weight of each edge in the graph by 1. Yeah, it should be correct because we are increasing each edge.
Yes, ma'am. Like we are increasing all the edges. Why it is not correct?
But
I'm
it
confused.
is possible that suppose there will be less number of edges in between. So I was thinking that suppose this is our 0, this is our 1, and suppose we are taking 4 to 5 vertices in between here, right? And just we are taking just one edge in between here. And suppose this cost is 1, 2, 3, 4. So what will be the sum is 10, right? 4. Yeah, 5 and 5 is 10. And suppose this weight is 11. Okay. And suppose my P is this path now. So suppose this is A, B, C, D, E. Okay. So now P is A to B, B to C, C to D, and D to E. Now the weight is here 10. Right? And now if I add +1 to every edge in the graph, here +1, here +1, also +1, +1. So now this P will have the weight 2 + 3 + 4 + 5, okay, which is more, and here +1, which is equal to 12. So now this the cost of this path P will be, this will be 9 and 11, 14, correct? Yeah, 14.
Yes,
But
ma'am.
now
So,
we have this path.
okay, I understood, ma'am. Then how is option D correct then? Like if we go like this, yeah, here we're
Okay,
doubling.
so suppose G is a weighted graph, the weight of all edges are positive. Okay, so let P be the shortest path from A to B. If we double the weight of every edge in the graph G, then the shortest path remains same, but the total weight of path changes. This should not be correct because we have a concrete example, right? Such scenario can be happen.
Okay, ma'am.
Because this is a example, correct? This graph can happen.
Yes,
This
ma'am.
weights
Yes, ma'am.
can happen. This is a question from mock. Is that the case?
No, ma'am. This is from practice assignment.
Practice assignment 11.
Yes, ma'am.
Okay, I'll check this question and
Yeah.
let you know.
Okay, ma'am.
Yeah, I'll check it out.
Ma'am,
Ma'am?
can you ask any of can we change the deadline of the mock test? Because if it is 21 and 22nd, we can't see that solutions, like, is it correct or wrong?
No, actually, we cannot change the deadline. So you can ask either Vishal sir. I'll ask him if we are able to change it or not.
Yes, ma'am, because if we see our answers, if it is wrong, we'll know the correct steps to do that.
But his
Okay,
point is
I'll let you know. I'll talk
because
to this with Vishal sir.
his point is correct now. But however, Sunday morning, if we come to know the mark solution, what is the use after the exam finished?
Yes, ma'am. What is the
Yes,
use of
ma'am.
writing mock test?
Yeah, that is what I'm feeling. But however, we can't change.
Ma'am, could you go to the other questions which I've sent?
Yeah, so
Could you go up from the starting where I've sent, because some questions are interconnected.
okay, so this one. Is this the question?
Yes, ma'am.
So what's your doubt in this?
Ma'am, I'm not able to get the right answer. Like I'm not able to.
So this is related to minimal cost spanning tree.
Yes, ma'am.
What is the total maintenance cost of the optimal subset of link? Okay.
Yeah, this is minimum cost only.
Minimum cost spanning tree. So we can.
We can do.
So start with the one. I'll always use Kruskal one. I think it's easy. So this will be the one edge. This will be the another edge. This will be the another edge. Okay, this is not the 3. We have to go to 2 only, na? We can choose 2 weight edge. Then we cannot choose 3 weight edge. We cannot choose, we can choose this 418 edge, then we cannot choose this 41. I can choose the 5.
Okay, now I got it, ma'am. Okay. Yeah, I made a mistake. I have chose third edge.
Okay.
I thought
Yeah,
it is forming a cycle, so I just skipped the second. Okay, yeah.
Any other doubt?
The above question, the above question,
Yeah.
which you just solved, the only last two questions.
Yeah, sure.
Ma'am, the PDF.
Okay, this one. Yeah, I'll share the PDF. Just wait
Yes,
for
ma'am. This
2
question.
minutes. So here, suppose there is adjacency metric of a connected undirected graph G. If A square is this, path between any two vertices has length at most 2, then which of the following may represent the graph G? So here you can consider, right? So yeah, just check the entry wise. So here the entry is 1, so that means every vertex we have to reach. Okay, so one thing you can do. See here the all diagonal entries are 1. So that means we should be able to travel from one vertex to that vertex. I mean back, something like this should happen.
This is undirected, right?
Yeah, this is undirected graph. And A square is given to you. So, and see, all the diagonal entries are 1. So what does diagonal entry says to us? So if A square of 1 comma 1 is equal to 1, so that means there is a path from vertex number 1 to vertex number 1 by going some another vertex 2.
Ma'am, I would like to clarify one thing. In A square, does it contain even does it contain even direct edges, or only the intermediate edges are contained in A square?
No, in A square means we need to find a path of length 2. So if the path has length 2, then there should be one vertex here and another vertex here. Something like this. This is the path of length 2. So if A square of something is 1, so that means those two vertices are connected by some particular edge. Some two edges.
Ma'am, then how would we reach from 1 to 1, like from one
Yeah,
edge
that's
to
the
one edge?
thing. I'm
This is
saying that yes,
the answer is please draw a line from top edge to bottom edge. That's the answer, ma'am, actually.
This one?
Yes, ma'am.
Okay.
At most 2, I'm not able to find like from one edge to itself, if we calculate.
See here, A square of I comma j, this is equal to 1. If there is a path between I and j, there is a path between I and j of length 2. Right? Not at most 2 or at least 2. Path between two vertices at length at most. Okay. So here they have mentioned at most 2. So at most 2 means okay, fine. This is not the case. It should be A3, if this is the answer. Because here we can reach every vertex to every other vertex using 3 length path, not 2 length path. There is some mistake in here, I guess.
This is a graded assignment question, ma'am. Even I am confused. Like, does
Because
anyone have
obviously
any
if we,
idea in the class, right? Ilango.
right. See here, one thing we can notice that the diagonal entry is 1, correct?
Yes,
so if the
ma'am.
diagonal entry is 1, so that means we have to reach from one vertex to that vertex using 2 edges. It is not possible, correct? I mean, it is possible, then such kind of scenario will happen. This is 1, this is 2. So we have to go to 1 to 2 and then come back. So this is not the case. And in this graph, you observe that we can reach from every vertex to the same vertex via using 3 edges. We can reach to this vertex going via this triangle, and reach to this vertex by going via this triangle. So here, there should be A cube. There should not be A square.
Yes, ma'am.
Things because A square doesn't make sense anymore. I have about to check. I haven't checked the graded assignment or practice assignment questions, but I'll check
And
and
from this
in
question,
the
Might be the case of unidirected edges.
sorry, what?
Might this be the case of unidirected graphs?
It's a case of which graph? Undirected graph, no?
undirected.
Undirected graph.
So yeah, it's a case of undirected graph, no?
Then isn't it possible to reach the same vertex using two paths, like back and forth, like you said?
But this is not a path. For me,
It's a edge
when you
only,
are
na?
saying 1 and 2 is connected by a single edge, so we can
Yeah.
go to 2 and then come back to 1. That means the path will be 1 to 2 and then 2 to 1.
Oh, yeah.
It's
It
not
is
a
not
two
a
edges
cycle
though.
something.
Yeah, it's a but in undirected graph, we don't consider such of cycles.
At least 3 elements.
Yeah, when we are using the same edge. Okay, I'll let you know about this question. I'm not sure.
Ma'am, can you draw the
Do-
matrices from a square to a cube? That is so confusing in the video too.
Okay, so if you want to just multiply a square to e cube, we have to go. But for that also, I need the information of a. If you want to draw a cube, then I need either a or I need a graph. Because then only I can go to from a square to a cube.
So we just need to multiply, na?
Yeah, we just need to multiply. One. Okay, I'll let you know about this question. I'm not sure it's
Okay, ma'am. Yeah, no
fully
problem.
wrong or something.
Ma'am, can you explain what exactly is a square? Because in PDF, they multiplied two matrices, A and A. But actually, it seems a square is like reaching
Path of two
another
elements from A
vertex
to B.
using two paths.
Hmm.
But in PDF, they have multiplied two AA matrices and called it a square.
Yeah, so a square is a into a, but here whatever algebra we applied Boolean algebra.
Right.
Right. So this is correct though.
But a cross a gives a different value than a square. If we call a
If
square,
we a square of I comma j, if we take, okay, but both things are same actually. So we have
Ma'am, it will
to,
result same if you multiply even A to in A
no,
to A.
they are different results. I'm getting different results.
it should be same because that's the conclusion we have made at the end, right? A square is nothing but a multiplied by a. AQ is nothing but a multiplied. They should be same. These both description should be same. I think we are doing some
If you have time,
mistakes.
can you please give an example of a simplified graph and calculate a square and first calculate a and then a square?
Okay, so let's see.
Just very simple, not some typical graph.
Yeah, this is so 1 is connected to 2 and 4. So 0, 1, 0, 1. It will be complicated if we compute. Let's take time and then this will be the adjacency matrix for this triangle, right? Every vertex is connected to every other vertex, but it's not connected to itself because of the self loop. Here, if we compute a square, now I think that diagonal makes sense. So that means they are considering the straight line only, whatever you guys said, that this path, that 1 to 2 and then 2 to 1. This is a 2-length path. Then only we will get a square is equals to a multiplied by a. 0, 1, 1, 1, 0, 1, 1, 1, 0. So 0 multiplied by 0 will be 0, 1 multiplied by 1, 1 multiplied by 1. So this will be 1. Now this will be 0, 0, 1. This will be 0, 1. 0 will be 1. Right? It will be 0 multiplied by 0. Ultimately, we get 1 because in every row there is one combination of 1 and 1. 0. Right. So ultimately we get a square to be equal to 1. Because although it's a triangle, so we can reach every vertex from every other vertex using 2 edges. So yes, they are considering this path to be a 2-edge path. If there is a, if one is connected to any other vertex 2, then we can take a path where we go to 1 to 2 and back to 2 to 1. This is our 2-length path. Okay, so if we assume this condition, then I think now that question makes sense to me. Okay, so here, so now diagonal entries are fine because we are considering this to be a path. So that means this diagonal is okay. Now from here a square of 1 comma 2 is also equal to 1. That means we can go to 1 to 2. So what you do, am I audible? Hello?
Yes, yes.
Yes, ma'am. Yes.
Yeah. So for solving this question, one simpler method is just take one example to be your graph and find out its a and then find out its a square. If it matches to this one, then that will be your answer. Because going from matrix to graph is a little bit tougher as compared to going from graph to the matrix.
The graph is 8 cross 8, I think. No, 6 cross 8.
Okay, then the graph is also.
6.
And you just have to find out this condition. There should be a 2-length graph from any vertex to n. For example, 1 is connected to 1. So for that, you have to either consider these first of all number these vertices. 6. Okay, so this is the answer now. So this was the answer, no? So what you'll do, just first of all, number all the vertices. 1, 2, 3, 4, 5, 6. Right? And here also number the rows. But still it will take time. I mean, you have to observe each entry and then you have to answer.
Ma'am,
We need to
here,
number properly, ma'am, because some entries are 0, right? Like we need to check
Right.
for which entry we can't just
Which
number
entries we
directly.
cannot find. Mhm. Yeah, that's the thing. Yeah, ultimately it required some time. Although it's not that easy, but it's lengthy. You have to judge entry by entry. Is there 2-length path or not?
And C is true
here
also.
actually the question mentioned the shortest part between any two vertices has length at most 2. So which means every vertices to other vertices, so I can reach by maximum 2 hops. So it seems we can observe from the graph which are the graph has from the out degree or in degree is 3, then it would be correct. So that is the shortest way to get that answer. Because
But
you
there's
can
an
observe
undirected graph.
whatever.
Those are undirected graphs, so in degree what
That
do
is
you
undirected.
Whatever. I mean saying the edges. So if it is,
Hmm.
it has to be connected at least 3 edges. Each vertex has to be connected because it has 2 hubs. So with other example of graphs which is having discrepancies on this,
Right.
I can reach all the vertices all with the other vertices with the 2 hubs maximum.
Yes, actually. Yes, Amrita, is there any doubt?
Excuse me,
Yes,
ma'am.
ma'am.
Yeah, Amrita, you can go.
You discussed a question previously that doubling the weights will change the shortest path, right?
Yeah.
But actually, the example you have considered, like the entries are the weights are 1, 2, 3, and 4 for one path.
No, not doubling, just adding one. Doubling
No, ma'am.
and
The option D also, like.
okay, in option D, they say doubling the weight, right?
Yeah, but doubling will not change the smallest path. Like if you have considered
doubling may
1,
not
2, 3,
change.
and 4,
Hmm.
and 11 as the other path, if you double them, 1, 2, 3, and 4, that path will give you, after doubling, 20, but 11 will give you the 22.
22. So I think doubling won't work, but adding the
multiplying a
one
factor will not change the shortest path.
will not change the shortest path.
Yeah, that is option D
I
is
thought
correct.
that's
That is what.
adding of two.
Yeah.
Option D is correct, ma'am.
Yeah, option D is correct.
Doubling is there, so then it's correct. I thought adding of two. So I thought adding of one won't work, so adding of two is also okay. So what does it say? P is the shortest path. If we double the weight of every edge in the graph C, then the
Yeah, you're
shortest
right.
path remains.
We are doubling it, yes.
We are doubling it, so it won't work. I thought we are adding two.
Excuse me, ma'am. The one
Can you
question.
please,
Says,
can you please do the question you guys are talking about? I will take a
The
screenshot.
Manish.
Actually, I've sent it to ma'am personally.
Yeah,
If
send
anyone
it to
if
everyone.
anybody wants, please go
Yeah.
and go back to the live session where you in YouTube.
Yeah.
Please, there you can
Okay.
get.
Okay.
Yes, is there any doubt?
ma'am,
Someone was saying something. Yeah. Okay, so we can end this session here. There is no doubt. Or else, if we have doubt, we can discuss in the next one.
Ma'am,
Thank you, ma'am.
Ma'am, one question is there.
Which
यार
question?
छोड़ दो यार.
Jatin is there, right?
Yes, ma'am, I have sent you personally. Ma'am, it's a small question, just need an idea.
Okay, suppose we perform Prim's algorithm on a graph G starting from vertex V1 to find the minimum from G. Then the order in which the vertices are added is. It's actually depend on the graph. We need graph. There should be a graph image, na?
Ma'am, above the adjacency matrix is given only.
Okay, adjacency. So create a graph using this adjacency matrix. Because adjacency, it's an easy one, right? So many entries are 0, and we just have 7 vertices. So we can easily create a graph. Just create a graph and apply the Prim's algorithm.
Okay.
Usually this revision session you are giving some examples to practice or exercise. Today you didn't give any exercise,
Okay.
or a sample.
Yeah, I think there are, you can see, I have discussed the pattern of the question, right? So you can practice some of those type of questions.
Sure,
Because
sure.
there are not much more type of graphs.
Done that. Thank you.
I'll upload the PDF and all the best for your entry.
excuse me, ma'am, this
you.
last one. Here we have a graph G which has 6 vertices. We write down the degrees of vertices in G in descending order. Which of the following is a possible listing of the degrees? How to attempt this question?
They have listed the degree in descending order, and you want to find out which of the possible ordering it can have.
Yes.
Okay, so for that, first thing is hand-checking lemma. Just find out that the sum of the degree should be matches as twice the number of edges. So that thing you can do, or else you can count the number of odd vertices. So this question actually based on that particular topic, hand-checking lemma. Number of odd vertices should be even. So these 2 or 3 things you can do, or just conceptually think that this kind of degree is possible or not. Right? Because if we want degree, we need edges. So for edges, we need some vertices should be there. Right?
Okay.
So just think about this. Either you can use hand-checking lemma, or just by thinking that it is possible or not.
Okay.
And can you explain the question number 3 of the image I have sent?
Yeah, sure. Question number 3, right? For what value of x can we use Bellman fold to find the shortest path? From the okay, so here, see, here if you add some x, then it is creating some cycle, right? So x, this edge x is a part of a cycle. The cycle is 1 to 4, 4 to 2, and 2 to 1. So you just have to take care that it should not create any negative cycle. Okay, so for example, if you take x to be equal to minus 14, then the weight of this particular cycle is minus 14 plus 4 and plus 3. That will be minus of 7, that means negative. So that's the thing you have to consider. You have to choose x in such a way that it should not create a negative cycle. Okay, so x value should be greater than or equal to 7 because the weight of this particular cycle is x plus 7. So you want x plus 7 is greater than or equal to 0. That means x should be greater than or equal to minus 7. Is it clear, Priyanshi?
Yes, ma'am. Thank you, ma'am.
Thank you guys for
Thank you.
joining.
Good night.
I upload the PDF.
Thanks, ma'am.
Thank you so much, ma'am. You've been a great help.